Most nights the sky looks calm, a scattering of stars, a faint haze where the Milky Way stretches across the darkness. Nothing about it suggests excess or abundance. And yet, every point of light belongs to a structure so vast that even the idea of counting similar structures elsewhere begins to strain intuition. From inside one galaxy, the universe feels sparse, empty even. Large distances dominate perception, not numbers. But as telescopes improved and surveys deepened, that sense of emptiness began to dissolve. Faint smudges multiplied. Deep images revealed thousands of galaxies where none had been visible before, and slowly a quiet problem emerged. How many galaxies are actually out there? Not how many stars, not how big the universe is in theory. But how many separate, gravitationally bound systems of stars exist within the part of the universe that can, in principle, be observed? A question that sounds simple, almost innocent, yet refuses to settle on a single number. Every attempt to answer it runs into limits of light, limits of distance, limits of definition. The further outward observations reach, the more galaxies appear, often smaller, fainter, and easier to miss. And beyond a certain point, even existence itself becomes something that must be inferred rather than seen. This video is not about rushing toward a final figure. It's about how astronomers approach the problem at all, how nearby galaxies inform distant ones, how surveys, deep fields, and simulations slowly build a picture that is always provisional, and why the universe seems content to reveal structure without ever offering completion. Welcome to the Sleepy Scientist. If this kind of slow, thoughtful exploration helps you unwind, consider liking the video and subscribing to the channel. And while you're settling in, let me know where you're watching or listening from. From inside a city under a dark sky, or somewhere in between. There's only one galaxy that can be experienced from the inside. Every other galaxy appears as a distant object, a patch of light against darkness, but this one surrounds the observer completely. Stars appear in every direction. Dust lanes stretch across the sky. A faint band of light arcs overhead on clear nights, marking the dense disk of the Milky Way seen from within. This embedded position feels intimate, even familiar, yet it quietly distorts perception in ways that are easy to overlook. From the inside, symmetry is difficult to judge, scale is hard to measure, completeness is almost impossible to assess. There is no external vantage point from which the full structure can be seen at once. Instead, the Milky Way must be reconstructed indirectly, star by star, region by region, using distance estimates, motion, and brightness as imperfect guides. That challenge shaped the earliest attempts to understand what kind of galaxy this actually is. At the beginning of the 20th century, astronomers attempted to map the Milky Way by counting stars in different directions. One of the most influential efforts came from Jacobus Kapteyn, who assembled one of the first systematic models of the galaxy using star counts and assumed brightness distributions. His model suggested a modest flattened system with the Sun located near its centre. It was elegant, mathematical, and deeply wrong. The error was not carelessness, it was invisibility. Interstellar dust absorbs and scatters light, especially in the plane of the galaxy where stars are most densely packed. Distant stars appeared dimmer not because they were few, but because their light was being quietly erased along the way. Kapteyn had no way to account for this properly. As a result, the Milky Way appeared smaller, neater, and more complete than it actually is. This early mistake matters because it reveals a deeper pattern. When observation depends on light alone, absence can masquerade as emptiness. What is not seen may still exist in large numbers. That lesson echoes through every later attempt to count galaxies beyond the Milky Way. As techniques improved, astronomers began to look not only at where stars were, but how they moved. Stellar motions offered a different kind of information, one less dependent on brightness alone. By tracking how fast stars orbited the galactic centre at different distances, it became possible to infer how much mass the galaxy contained and how that mass was distributed. This is where rotation curves enter the story. When orbital speed is plotted against distance from the centre of a galaxy, classical physics predicts a steady decline beyond the region containing most of the visible matter. Instead, observations showed something unexpected. Stars far from the centre were moving just as fast as those closer in. The galaxy behaved as though it contained far more mass than could be seen. Vera Rubin's careful measurements of galaxy rotation curves made this discrepancy impossible to ignore. The implication was not a minor correction, but a structural revision. A galaxy was no longer just the sum of its visible stars and gas. It was embedded in a vast halo of unseen mass, now known as dark matter, extending far beyond the luminous disk. This changed what it meant for something to qualify as a galaxy. A galaxy was not defined solely by light. It was defined by gravitational coherence, by the presence of a massive structure capable of binding stars together over billions of years. Suddenly, the visible portion became only a tracer, not the whole. From inside the Milky Way, this realization complicates everything. The bright spiral arms that dominate the night sky represent only a fraction of the system's true size and mass. Surrounding them is a dark matter halo stretching several times farther than the visible disk. Embedded within that halo are globular clusters, streams of stars from long-past mergers, and satellite galaxies so faint they barely register against the background. If the full extent of the Milky Way cannot be seen directly from within, then any attempt to use it as a template for other galaxies must proceed cautiously. What appears complete may be partial. What appears typical may be biased by perspective. Internal uncertainty accumulates quietly. Distances to stars carry error margins. Dust distribution varies irregularly. Stellar populations overlap in projection. Even basic quantities such as total stellar mass and diameter are revised as new data arrives. Each uncertainty is manageable on its own, but together they remind the listener that the Milky Way is not a known object in the everyday sense. It is a model, refined continuously, never finished. This matters deeply when the goal is to extrapolate outward. Counting galaxies elsewhere relies on assumptions about what galaxies generally look like, how massive they tend to be, and how their light relates to their total mass. If the home reference point is itself only partially understood, then every larger estimate inherits that uncertainty. There is also a subtler issue. Living inside a large spiral galaxy normalizes largeness. Spiral arms feel common because they dominate nearby views. Dense star fields feel typical because they fill the sky. Yet when the local universe is examined more broadly, massive spirals turn out to be relatively rare. Smaller galaxies, faint galaxies, and irregular systems dominate by number, even though they are easy to overlook. The Milky Way is not misleading because it is unusual, but because it is prominent. Its brightness and size command attention in a way that smaller systems do not. From the inside, that prominence can feel like a baseline, when it is actually an outlier in some respects. So the very first step in asking how many galaxies exist is not outward, but inward. It begins with recognizing that even the nearest, most familiar galaxy is only partially visible, partially understood, and deeply shaped by perspective. The problem of counting galaxies does not begin at the edge of the observable universe. It begins here, inside a system that hides a significant fraction of itself from its own inhabitants. Once that is accepted, the wider problem becomes easier to frame, even if it does not become easier to solve. When attention moves just beyond the Milky Way, the first galaxies that come into view are not subtle. The Andromeda Galaxy dominates the nearby sky in scale and presence, stretching across a region several times the width of the full moon when observed under dark conditions. It is massive, bright and structured, with sweeping spiral arms and a dense central bulge. Slightly farther away sits the Triangulum Galaxy, smaller but still clearly defined, another spiral system with visible organization and ongoing star formation. Together, these neighbors feel familiar. They look like galaxies are supposed to look: large, orderly, bright enough to announce themselves even at great distances. And for a long time, that familiarity shaped intuition in a quiet but powerful way. When the nearest examples resemble one another, it is tempting to assume they are typical. The Milky Way, Andromeda, and Triangulum all belong to the same broad class of spiral galaxies. They contain hundreds of billions of stars, rotating disks and extended halos of gas and dark matter. Studying them side by side creates the impression that galaxies, in general, are large, luminous, and easily recognizable. That impression turns out to be misleading. Before that became clear, however, astronomers had to answer a more basic question. How far away are these neighboring systems really? The difference between a galaxy being a few 100,000 light-years away or several million light-years away completely changes how its size and brightness are interpreted. This is where refinements to the distance ladder reshaped understanding. The distance ladder is a collection of overlapping methods used to estimate cosmic distances, each calibrated against the next. Cepheid variable stars play a central role at nearby scales, because their intrinsic brightness is linked to their pulsation period. Once that relationship was established, Cepheids became reliable beacons for measuring distances to nearby galaxies. Alan Sandage devoted much of his career to refining these measurements, improving calibrations, reducing systematic errors, and clarifying which distance indicators could be trusted at different ranges. His work helped stabilize estimates of how far away Andromeda and Triangulum actually are, placing them firmly outside the Milky Way and anchoring the scale of the local universe. With distances better constrained, comparisons became more meaningful. Andromeda emerged as slightly larger and more massive than the Milky Way, while Triangulum appeared smaller and less evolved, yet still clearly a spiral galaxy. These differences were interesting, but they did not immediately challenge the underlying assumption that spiral galaxies represented the standard model. That assumption was reinforced by visibility. Large spirals are bright, their stars are numerous, their gas clouds glow, their shapes stand out clearly against the darkness of space. When telescopes sweep the nearby universe, these systems demand attention simply because they are easy to see. Visibility, however, is not the same as abundance. This distinction is subtle at first. When catalogues of nearby galaxies were assembled, the most prominent objects naturally filled the pages. Spirals with clear structure dominated early lists, not because they were most common, but because they were easiest to identify at distance. Smaller, fainter systems blended into the background, often dismissed as noise or ignored entirely. The result was a skewed picture of the galactic population. If attention is drawn primarily to luminous spirals, then spirals begin to feel typical. If spirals feel typical, then estimates of how many galaxies exist begin to scale from that expectation. Bright galaxies become the reference point and everything else becomes an afterthought. This bias is not a failure of reasoning. It is a consequence of how light behaves. Bright objects announce themselves across space. Dim objects do not. A small galaxy containing a few million stars can be overwhelmed by foreground stars, dust, or background glow. At even modest distances, such a system may vanish entirely from view. In contrast, Andromeda would remain visible even if it were several times farther away. Its sheer size and brightness granted a kind of observational privilege. That privilege distorts intuition. When galaxy populations are examined statistically, a different picture emerges. Massive spirals like the Milky Way and Andromeda are impressive, but they are not numerous. They occupy a small fraction of the total galaxy count. Most galaxies are far smaller, far dimmer, and far easier to miss. This is where Triangulum quietly becomes more informative than it first appears. Though still a spiral, it is significantly less massive than its two larger neighbours. Its lower stellar mass and simpler structure hint at a broader population of modest galaxies that do not dominate their surroundings. Even Triangulum, however, remains relatively bright compared to the faintest systems nearby. The similarity among the nearest large galaxies once encouraged the idea of galactic uniformity. It suggested that galaxies formed in broadly similar ways, grew to comparable sizes, and followed predictable evolutionary paths. That view simplified early models and made the universe feel more orderly. As surveys expanded and sensitivity improved, that simplicity began to unravel. The local universe revealed a menagerie of systems that did not resemble spirals at all. Irregular galaxies with chaotic shapes, elliptical galaxies lacking disks entirely, dwarf galaxies barely holding themselves together gravitationally. Many of these systems were found not in isolation, but clustered around larger galaxies like satellites, their existence overshadowed by the brilliance of their hosts. This realization forces a recalibration of intuition. The galaxies that dominate attention are not the ones that dominate numerically. They are statistical outliers in terms of mass and brightness, even though they feel central to experience. The nearest neighbours, then, play a dual role. They provide essential calibration points for distance, structure, and dynamics. At the same time, they quietly mislead by overrepresenting a particular class of galaxy. Without careful correction, they encourage overconfidence in patterns that do not generalize. Recognizing this is an important step. It marks the moment when the problem of counting galaxies shifts from identifying prominent objects to accounting for populations that do not announce themselves. The universe does not hide most of its galaxies deliberately. It simply makes them easy to overlook. Once that is understood, attention naturally begins to drift away from the brightest neighbours and toward the smaller, quieter systems that surround them. Those systems, though less impressive individually, hold the key to understanding how many galaxies truly exist. Galaxies rarely exist alone. Although it is tempting to imagine them scattered independently through space, most galaxies are born, evolve, and persist within shared gravitational environments. These environments shape how galaxies form stars, how they grow, how they lose material, and how long they survive as distinct systems. To understand how many galaxies exist, it is not enough to count individual objects. It becomes necessary to understand the systems they belong to. This is where the local group becomes more than a convenient label. It is not simply a list of nearby galaxies. It is a gravitationally bound, evolving system spanning several million light-years, held together by the combined mass of its largest members and their extended dark matter halos. The Milky Way and Andromeda dominate this system. with Triangulum contributing additional mass, while dozens of smaller galaxies orbit, drift, and interact within the same shared gravitational landscape. Thinking in terms of a group immediately changes the nature of counting. Galaxies inside a group do not behave as isolated objects. Their histories overlap, their futures are intertwined, their present appearances often reflect past encounters rather than intrinsic properties. This perspective has been explored in depth by researchers such as Yuri Efremov, whose work emphasized the importance of environment in shaping stellar populations and star formation histories. Rather than treating galaxies as closed systems, this approach treats them as participants in a dynamic network of gravitational influence. In doing so, it reframes how galaxy population should be interpreted. Within the local group, interactions are not rare events. They are a defining feature. Satellite galaxies pass repeatedly through the outer regions of larger hosts. Tidal forces stretch them, compress them, and sometimes tear them apart. Gas can be stripped away, shutting down future star formation. Stars can be pulled into elongated streams that wrap around larger galaxies, leaving visible scars of past encounters. These processes directly affect visibility. A dwarf galaxy that once contained active star formation may fade after losing its gas, becoming harder to detect against the background. Another may be stretched so thin that it no longer resembles a galaxy at all, blending into stellar debris. From a purely observational standpoint, such systems are easy to miss or misclassify. This matters because dwarf galaxies dominate galaxy populations by number. In the local group alone, more than 50 small galaxies are known, and new ones continue to be discovered as surveys improve. Many of these systems contain only a few million stars, compared to the hundreds of billions found in the Milky Way. Individually, they are unimpressive. Collectively, they define the population. The local group demonstrates something fundamental. The smallest meaningful unit for galaxy statistics is not the individual galaxy, but the group environment. Counting galaxies without accounting for their interactions risks double counting some systems and missing others entirely. For example, when a dwarf galaxy is disrupted and its stars become part of a stellar stream, should it still be counted as a galaxy? At what point does it cease to exist as a separate object? These questions are not philosophical curiosities. They directly influence population estimates. If only intact, star-forming galaxies are counted, then many systems are excluded. If remnants and transitional objects are included, the number rises. The group context determines which interpretation makes sense. There is also the problem of survival time. Galaxies within groups have finite lifetimes as independent systems. Over billions of years, smaller galaxies tend to merge with larger ones, or dissolve under tidal forces. The local group is not static. It is slowly evolving toward fewer, larger galaxies through mergers and accretion. This means that the number of galaxies present at any given moment is not representative of how many galaxies have existed over time. Groups reduce galaxy counts as they age. A snapshot taken today captures only the survivors. From a statistical standpoint, this introduces a strong bias. Older groups will contain fewer galaxies than younger ones, even if they began with similar populations. Counting galaxies without considering group age and interaction history leads to misleading comparisons across cosmic environments. Isolated galaxy counts suffer from another problem. Truly isolated galaxies are rare. Most systems that appear isolated are simply distant from obvious neighbors or located in low-density regions. Even these galaxies are often embedded in faint filaments of dark matter and gas, subtly influencing their evolution. By contrast, the local group offers a relatively complete laboratory. Distances are well measured. Individual stars can be resolved in many member galaxies. Tidal features can be observed directly. This makes it possible to trace interactions with unusual clarity. Yet even here, completeness is elusive. Some dwarf galaxies remain hidden behind dust in the plane of the Milky Way. Others are so diffuse that they blend into the background. The known population is almost certainly incomplete. This reinforces a crucial point. If the nearest and best-studied galaxy group cannot be fully catalogued with confidence, then more distant groups are guaranteed to be incomplete. Their faintest members slip below detection thresholds. Their disrupted remnants are impossible to recognize. Counting galaxies as isolated points ignores these realities. It treats galaxies as static, independent units, when in fact they are transient structures shaped by collective dynamics. The local group shows that galaxy populations are not merely about formation. They are about survival. They depend on mass, environment, timing, and chance encounters. A galaxy's visibility today reflects not only what it is, but what it has endured. This is why galaxy groups are the smallest meaningful units for population statistics. They capture the context that determines which galaxies remain visible and which quietly vanish. Without that context, any count becomes an illusion of precision. Once this is understood, the task of counting galaxies expands again. It is no longer about tallying dots of light. It becomes an effort to account for systems in motion, shaped by shared gravity, evolving together over immense spans of time. And that makes isolated galaxy counts not just incomplete, but fundamentally misleading. If galaxies were counted by size or brightness alone, dwarf galaxies would barely register. They are small, faint, and often irregular in shape. Many contain only a few million stars, sometimes fewer, compared to the hundreds of billions found in large spirals like the Milky Way. From a distance, they fade quickly into the background, easily lost among foreground stars, dust, and noise. Yet despite their modest appearance, dwarf galaxies dominate the universe by number. In any reasonably complete survey, dwarfs outnumber large galaxies by a wide margin. They are not rare exceptions. They are the default outcome of galaxy formation. Large spirals and ellipticals draw attention because they are dramatic and luminous, but dwarfs are the quiet majority, forming wherever small concentrations of gas collapse inside dark matter halos. For a long time, this dominance was easy to underestimate. Early galaxy catalogues were built around what telescopes could see clearly, and what they could see clearly were bright extended systems. Dwarf galaxies slipped through the gaps, not because they were uncommon, but because they were observationally fragile. That fragility became impossible to ignore in the early 2000s, when new wide-field digital surveys began to probe the sky with unprecedented sensitivity. As these surveys expanded, something unexpected happened. The number of known nearby dwarf galaxies began to climb steadily, not because the universe had changed, but because the threshold for detection had shifted. Beth Willman played a key role in this transformation through the discovery and characterization of ultra-faint dwarf galaxies orbiting the Milky Way. These systems are among the dimmest galaxies known, containing as few as a few thousand stars spread over regions hundreds of light-years across. Their total luminosity can be less than that of a single bright star cluster, yet their internal motions reveal that they are embedded in dark matter halos massive enough to qualify as galaxies. The existence of these ultra-faint dwarfs exposed a crucial limitation in earlier counts. Galaxies have been missing not because they were hidden far away, but because they were barely luminous at all. Once survey sensitivity improved, these systems began to appear in large numbers, often clustered around larger galaxies. This discovery highlighted an uncomfortable truth. The number of galaxies one finds depends strongly on how faint one is able to look. Lower the detection threshold, and the count rises. Raise it, and the universe appears simpler and emptier than it really is. Dwarf galaxies are not just faint, they are also vulnerable. Their low masses make them susceptible to tidal stripping when they orbit larger galaxies. As they pass through the gravitational field of a massive host, stars can be pulled away, gas can be removed, and the remaining system can be stretched into elongated shapes. Over time, some dwarfs lose so much material that they are reduced to stellar streams, no longer recognizable as self-contained galaxies. This introduces the idea of a survival threshold. Below a certain mass, a galaxy cannot retain its stars and gas against external forces. It may form, but it will not persist for long. Above that threshold, it can survive repeated interactions and remain visible for billions of years. The exact value of this threshold depends on environment. A dwarf galaxy in isolation may survive with far less mass than one orbiting close to a giant spiral. This means that the same type of galaxy can have very different lifetimes depending on where it lives. From a counting perspective, this matters enormously. Some dwarf galaxies exist only briefly as identifiable systems, others persist quietly for cosmic timescales. A snapshot taken at any given moment captures only those that have survived up to that point. There's also the problem of classification. Many dwarf galaxies blur the line between galaxies and star clusters. Both can contain similar numbers of stars. Both can appear compact or diffuse. The key difference lies in gravitational binding and dark matter content, neither of which is directly visible. In practice, astronomers rely on stellar motions to make this distinction. If stars move too fast to be held together by their visible mass alone, the presence of dark matter is inferred, and the object is classified as a galaxy. If not, it is usually labelled a star cluster. This sounds straightforward, but in reality it is messy. Measurements are uncertain, sample sizes are small, boundaries are fuzzy. As a result, some objects sit uncomfortably between categories, included in some galaxy counts and excluded from others. Each of these decisions nudges the total number up or down. Dwarf galaxies also challenge intuitive ideas about shape and structure. Many lack clear disks or bulges. Some appear irregular, with star formation occurring in scattered regions rather than organized patterns. Others are spheroidal, containing old stars and little gas, their active phases long over. These differences are not cosmetic. They reflect distinct evolutionary paths shaped by environment, mass, and timing. When counting galaxies, treating all dwarfs as a single category can obscure this diversity, while splitting them too finely can inflate uncertainty. What remains consistent is their sheer abundance. In galaxy groups like the local group, dwarfs outnumber large galaxies by at least an order of magnitude. In richer environments such as galaxy clusters, the imbalance is even more extreme. This has a direct and unavoidable consequence for estimates of how many galaxies exist in the universe. If most galaxies are small and faint, then most galaxies are difficult to detect. Any survey that misses faint objects will systematically undercount the total population. As detection limits improve, counts rise. As classification criteria broaden, counts rise again. This is not a sign of error or indecision. It is a reflection of the underlying population. The universe does not consist of a modest number of grand structures surrounded by empty space. It consists of vast numbers of modest systems, many hovering near the edge of detectability, many shaped or damaged by their surroundings, many short-lived on cosmic timescales. Dwarf galaxies are the statistical backbone of galaxy counts. They set the scale, they dominate the numbers, and they quietly ensure that any attempt to count galaxies must remain provisional. When astronomers revise estimates upward, dwarfs are almost always the reason. Not because new physics has been discovered, but because the universe turns out to be more crowded at small scales than intuition suggests. Understanding this shifts the question of how many galaxies exist away from dramatic extremes and towards subtle limits. It becomes less about how far telescopes can see, and more about how faint a system can be and still be recognized as a galaxy at all. That recognition, fragile and conditional, is what keeps the total number rising. At first glance, the word galaxy feels unambiguous. A galaxy sounds like a clearly defined thing, a large system of stars held together by gravity, distinct from its surroundings and recognizable when seen. In practice, however, that clarity dissolves very quickly. Astronomers do not count galaxies the way one might count planets or moons. Before anything can be counted, it must be defined, and that definition turns out to be far more slippery than intuition suggests. One way to define a galaxy is through its dynamics. A galaxy must be a gravitationally bound system, meaning its stars move in ways that indicate they are held together by a shared mass. This criterion immediately excludes many loose associations of stars that appear clustered but are not truly bound. It also elevates the importance of stellar motions, because motion reveals mass, including mass that cannot be seen. Another approach focuses on stellar populations. A galaxy typically contains multiple generations of stars, often spanning billions of years in age. This suggests a long-lived system capable of forming stars repeatedly over cosmic time. By contrast, many star clusters form stars in a single burst and then fade. That difference sounds straightforward, but in small systems the distinction can blur. Dark matter content adds yet another layer. Modern definitions often require a galaxy to be embedded in a dark matter halo. This criterion is especially important for dwarf galaxies, where the visible stars account for only a small fraction of the total mass. If stars are moving too quickly to be explained by their own gravity alone, dark matter is inferred, and the system is classified as a galaxy. Each of these definitions captures something real, but none is complete on its own. Some systems satisfy all criteria, others satisfy only one or two. The question then becomes which properties matter most. These ambiguities were explored in depth by astronomers such as Sidney van den Berg, who spent decades analysing galaxy morphology and classification. His work highlighted how easily galaxies resist tidy categorization. Even among large systems, shapes vary smoothly rather than falling into discrete boxes. Among smaller systems, the boundaries become even more porous. Van den Berg showed that classification schemes are not neutral descriptions. They encode assumptions about formation, evolution, and importance. When those assumptions change, the categories change with them. This has a quiet but powerful effect on galaxy counts. When astronomers publish estimates of how many galaxies exist, those numbers often differ not because the observations disagree, but because the definitions do. One study may include ultra-faint dwarfs as galaxies. Another may exclude them as star clusters. A third may classify the same object differently based on new data about stellar motions. Each choice is defensible. Each choice alters the final count. These shifts rarely make headlines. They occur in footnotes, tables, and methodological sections. Yet collectively, They move the number of known galaxies up or down by significant margins. The problem becomes even clearer when considering how galaxies support themselves against gravity. Some galaxies are rotation supported. Their stars orbit a central axis in an organized disk, like the Milky Way or Andromeda. Rotation provides stability, and the system's structure is relatively easy to interpret. Others are pressure supported. In these systems, stars move in many directions, held together not by coherent rotation, but by the collective effect of random motions. Elliptical galaxies and many dwarf spheroidals fall into this category. Their shapes are smoother, their dynamics less intuitive, and their boundaries harder to define. Pressure-supported systems challenge simple ideas of what a galaxy looks like. They may lack clear edges. Their stars fade gradually into surrounding space. In some cases, it is unclear where the galaxy ends and the background begins. This matters for counting. A rotation-supported disk presents a clear signal. A pressure-supported cloud of stars does not. Detection becomes sensitive to how far out one draws the boundary, which stars are included, and which are dismissed as foreground or background contamination. The issue grows sharper at small scales. Some ultra-faint systems contain only a few thousand stars. Their internal motions suggest dark matter, but the measurements are noisy. Their stellar populations resemble those of large star clusters. Their shapes are irregular. Classifying them requires judgment as much as measurement. Different research groups sometimes reach different conclusions about the same object. One catalogue lists it as a galaxy, another lists it as a cluster. Neither is obviously wrong. They're applying different thresholds. This is why taxonomy becomes a limiting factor in galaxy counting. The universe does not present galaxies as neatly labelled entities. It presents a continuum of structures, ranging from massive luminous spirals to barely bound stellar assemblages hovering on the edge of coherence. Counting requires drawing lines across that continuum. Those lines are not arbitrary, but they are not uniquely determined either. They reflect the current state of theory, the available data, and the questions being asked. A study focused on dark matter distribution may adopt one definition. A study focused on star formation history may adopt another. As a result, the number of galaxies is not a single objective fact waiting to be discovered. It is a quantity that emerges from a set of choices, each grounded in physical reasoning but none immune to revision. This does not mean galaxy counts are meaningless. It means they are conditional. They describe how many galaxies exist according to specific criteria, within specific observational limits, at a particular moment in scientific understanding. There is a quiet irony here. As telescopes improve and data becomes richer, the problem does not simplify. It becomes more detailed. More objects appear near the boundary. More exceptions demand explanation. More systems resist clean classification. In a sense, the universe becomes more crowded and less tidy at the same time. This is why published galaxy counts tend to be ranges rather than precise totals. They acknowledge that definitions matter. They admit that some objects sit uncomfortably between categories. They reflect humility rather than uncertainty. When astronomers say there may be hundreds of billions or even trillions of galaxies, that statement carries an implicit clause. It depends on what is counted, how faint is too faint, and where the line between galaxy and non-galaxy is drawn. Understanding this reframes the question itself. Asking how many galaxies exist is not just a question about abundance. It is a question about identity. It asks what kind of structures are considered meaningful, persistent, and worthy of a name. The answer evolves because the universe is more inventive than classification schemes, and every time those schemes are refined, the count shifts quietly in response. There was a time when galaxies did not exist as a category at all. The night sky contained stars, planets, and a scattered collection of faint misty objects known collectively as nebulae. Some were clearly associated with star formation inside the Milky Way. Others were unresolved smudges whose nature was unclear. Through the telescopes of the 19th century, they all looked broadly similar. Soft edges, no obvious stars, no reliable sense of distance. Without distance, size is meaningless. Without size, classification collapses. Astronomers could describe where these nebulae appeared in the sky, how bright they seemed, and sometimes how their light was distributed, but they could not say what they actually were. A faint spiral shape might indicate a nearby cloud of gas or an unimaginably distant stellar system. Both interpretations fit the data equally well. This ambiguity was not a failure of imagination. It was a limitation of tools. Telescopes of the time gathered relatively little light. Long exposures were difficult. Detectors were crude. Even large instruments struggled to resolve individual stars beyond the immediate surroundings of the Milky Way. As a result, many nebulae remained unresolved, their true nature hidden behind the same haze that made them intriguing. The problem was compounded by scale. If spiral nebulae were part of the Milky Way, then the galaxy itself would have to be enormous, extending far beyond the distribution of visible stars. If they were external systems, then the universe would suddenly become vastly larger than previously imagined. Both possibilities were unsettling, and neither could be tested decisively with the instruments available. Into this uncertainty stepped a different kind of observation. Rather than asking how nebulae looked, Vesto Slipher began asking how they moved. At the Lowell Observatory in the early 1900s, he turned a spectrograph towards spiral nebulae and measured their spectral lines with extraordinary care. What he found was unexpected. Many of these nebulae exhibited large Doppler shifts. Their spectral lines were displaced in ways that indicated motion at hundreds of kilometers per second, far faster than the typical motions of stars within the Milky Way. Some appeared to be approaching rapidly. Most appeared to be moving away. At the time, there was no accepted framework to interpret this. Cosmic expansion had not yet been proposed. The idea that the universe itself might be growing larger was not part of mainstream astronomy. Slipher's measurements stood alone, precise but puzzling. If spiral nebulae were small objects within the Milky Way, such extreme velocities would be difficult to explain. Stars orbiting the galactic center move at a few hundred kilometers per second at most, and those motions follow predictable patterns. The nebulae did not fit comfortably into that picture. Slipher did not claim to have discovered galaxies. What he provided was something more subtle and more important. He provided evidence that these objects were dynamically distinct from the stars around them. They behaved as though they were separate systems, not local clouds. Even so, interpretation lagged behind observation. Many astronomers continued to classify spiral nebulae as internal features of the Milky Way. Others argued they were external systems. The debate persisted not because one side ignored the data, but because the data were incomplete. Velocities alone could not establish distance. Without distance, size and nature remained ambiguous. This misclassification had a significant consequence. If spiral nebulae were assumed to be internal, then they were not counted as separate galaxies. They were treated as substructures within a single, large system. Population studies stalled because there was, by definition, only one galaxy to study. This bottleneck delayed the emergence of galaxy statistics by decades. Instrument limits played a decisive role. Early photographic plates were insensitive to faint stars. Even if a spiral nebula contained billions of stars, those stars would blur together into a smooth glow unless they were individually resolved. Only the nearest systems could be broken apart into discrete points of light, and even then only under ideal conditions. Dust further complicated matters. Dark lanes within the Milky Way obscured large portions of the sky, particularly along the galactic plane where many nebulae were observed. A distant galaxy viewed through dense dust could appear small and faint, easily mistaken for a local object. The universe was not only large, it was cluttered with obstructions. As telescopes improved incrementally, the picture shifted slowly rather than dramatically. Larger mirrors collected more light. Better optics improved resolution. Longer exposures revealed structure within some nebulae. Spiral arms became clearer. Bright knots appeared, suggestive of star-forming regions. Yet even these improvements did not settle the question. Structure alone could not distinguish between a nearby cloud and a distant galaxy. Nature, inconveniently, can produce similar patterns at very different scales. The turning point required a new kind of measurement, something that tied brightness to intrinsic properties rather than appearance, something that could break the distance deadlock. That solution would come from variable stars, whose predictable behavior allowed astronomers to measure distances far beyond the reach of parallax. But before that breakthrough arrived, the universe existed in a kind of conceptual limbo. Galaxies were there, but unnamed. Countless stellar systems existed beyond the Milky Way, but they were hidden inside a category that blurred the near and the far together. The universe was already crowded, but it looked sparse. This period of ambiguity shaped how astronomers thought about the cosmos. It encouraged caution. It reinforced the idea that classification must wait for measurement. It also left a legacy of humility that still matters. The lesson is straightforward but easy to forget. Observations do not speak for themselves. They are filtered through instruments, assumptions, and available frameworks. When tools are limited, interpretation narrows accordingly. The recognition of galaxies as separate worlds did not happen because the universe changed. It happened because the means to distinguish distance, motion, and structure finally converged. Once that convergence occurred, the population of the universe expanded almost overnight, not in reality but in understanding. Before that moment, galaxies were not rare. They were simply invisible as galaxies. And that invisibility reminds us that any count of cosmic structures is inseparable from the tools used to reveal them. For years, the argument over spiral nebulae was not about imagination or belief. It was about method. The disagreement that later became known as the Great Debate was, at its core, a clash between different ways of reasoning from incomplete data. One side argued from the distribution of stars and globular clusters within the Milky Way, concluding that the galaxy was vast enough to contain all known nebulae. The other side focused on the appearance and motions of spiral nebulae, suggesting that they were separate systems far beyond the Milky Way's boundaries. Both positions were grounded in evidence. Both relied on assumptions that seemed reasonable at the time. What neither side possessed was a reliable way to measure distances on truly extragalactic scales. Without distance, everything else remained uncertain. A spiral nebula could be small and nearby, or enormous and distant. Its brightness alone could not resolve the ambiguity. Structure did not help either, since nature has a habit of repeating patterns at different scales. The debate persisted not because the data were ignored, but because they were insufficient. The breakthrough came from a source that initially had nothing to do with galaxies at all. Henrietta Leavitt was studying variable stars in the Small Magellanic Cloud, a faint companion system near the Milky Way. While analysing photographic plates, she noticed a simple but profound relationship. Certain variable stars, later known as Cepheid variables, exhibited a tight connection between the period of their brightness variations and their intrinsic luminosity. The longer the period, the brighter the star truly was. This relationship transformed Cepheid variables into cosmic distance markers. By measuring how long a Cepheid took to brighten and fade, its true brightness could be inferred. Comparing that intrinsic brightness to how bright it appeared allowed its distance to be calculated. Crucially, this method did not depend on the star's location within the Milky Way. It could be applied anywhere Cepheids could be observed. Once this relationship was calibrated using nearby Cepheids with known distances, it became a ladder rung that extended far beyond previous limits. Distances that were once speculative could now be measured with confidence. When Cepheid variables were identified inside spiral nebulae, the implications were immediate and unmistakable. The distances derived were far too large for these objects to reside within the Milky Way. They were millions of light years away, placing them well outside any plausible boundary of the galaxy. This was not a gradual shift. It was a step change. Overnight, the universe expanded from a single galaxy to a population of many. Objects that had been treated as internal features suddenly became independent stellar systems, each comparable in scale to the Milky Way itself. The shock was not just quantitative, it was conceptual. The Milky Way was no longer the universe. It was one example among many. A large example, certainly, but no longer central by definition. The night sky, once interpreted as a sparse arrangement of stars with a few local curiosities, became a window into a universe densely populated with galaxies. This reframing immediately altered the problem of counting. Before this recognition, the number of galaxies was effectively 1. Afterward, it was suddenly unbounded. Every spiral nebula became a candidate galaxy. Every faint smudge raised new questions. The universe did not merely contain more structure, it contained orders of magnitude more structure. Importantly, this moment did not deliver closure. It delivered disorientation. Astronomers now faced a universe far larger than expected, populated by objects that could not yet be counted systematically. Telescopes could identify some nearby galaxies, but the vast majority remained beyond reach. The question shifted from what galaxies were to how many there might be. This transition marked the birth of galaxy demographics. Once galaxies were recognized as separate worlds, it became possible to ask statistical questions. How many galaxies exist nearby? How many are large or small? How they are distributed in space? Whether the Milky Way is typical or unusual? These questions could not have been meaningfully posed before the distance scale was established. They depended on galaxies being comparable objects, rather than ambiguous nebulae. The Great Debate is sometimes remembered as a contest with a winner and a loser. That framing misses the point. The debate was resolved not by argument but by measurement. Neither position collapsed under criticism. It was overtaken by new data. The resolution also revealed a recurring pattern in astronomy. Progress often arrives not as a refinement of existing ideas, but as a redefinition of what is being discussed. Once galaxies were recognized as independent systems, the entire vocabulary of the field changed. The Milky Way became one galaxy among many. Nebulae became galaxies. The universe became structured on scales that demanded new theories and new tools. There is a subtle consequence of this shift that matters for counting. Early galaxy counts were built on a sense of astonishment. Each new galaxy discovered felt like a revelation. Catalogues grew rapidly as telescopes improved, but there was no clear sense of completeness. The sky seemed to offer endless new systems, This sense of abundance was real, but it was also uneven. Bright, nearby galaxies were catalogued first. Faint, distant ones lagged behind. The distribution of known galaxies reflected observational reach rather than true population. Still, the recognition of galaxies as separate worlds changed the baseline permanently. Counting galaxies was no longer about expanding the Milky Way. It was about mapping a population. The scale shock lingered. Even as astronomers became accustomed to thinking in terms of millions of light years, the full implications continued to unfold. If nearby space contained dozens of galaxies, how many lay beyond? If telescopes revealed more with each improvement, was there any limit at all? These questions did not arise from speculation. They emerged directly from measurement. The universe had revealed itself to be far larger than expected, and that revelation carried a burden of uncertainty. The beginning of galaxy demographics did not provide numbers. It provided a framework, a way of thinking about galaxies as a population rather than a curiosity, a recognition that abundance, not isolation, defined the cosmos. From that point on, every improvement in observation added to the count. Not because galaxies were appearing out of nowhere, but because the means to recognize them were steadily improving. The discovery that galaxies are separate worlds did not answer how many exist. It made the question unavoidable. Once the universe was understood to contain many galaxies, counting them became a central challenge rather than a philosophical aside. And that challenge has been unfolding ever since, shaped by tools, definitions, and the quiet reminder that the universe is rarely as simple as first impressions suggest. Once galaxies were recognized as separate systems, the next impulse was straightforward. Count them. If the universe contained many galaxies rather than one, then it should be possible, at least in principle, to catalogue them, tally them, and arrive at a meaningful total. Early astronomers approached this task with the tools they had, and for the first time, those tools included the ability to record the sky systematically. Photographic plates transformed astronomy in the late 19th and early 20th centuries. Unlike the human eye, a photographic plate could collect light over long periods of time, accumulating faint signals that would otherwise be invisible. Exposures lasting hours revealed countless dim objects scattered across the sky, many of them spiral nebulae now understood to be galaxies. These plates made repetition possible. The same region of sky could be recorded, studied, compared, and catalogued. Patterns began to emerge. Certain regions appeared richer in galaxies than others. Some galaxies clustered together, while others appeared more isolated. Early catalogues were assembled from these images, listing galaxy positions, apparent brightness, and rough shapes. For the first time, the universe began to look like something that could be inventoried. But the appearance of order concealed deep limitations. Photographic plates had finite sensitivity. They responded strongly to blue light and weakly to red light. Faint galaxies with older stellar populations emitting more red light were underrepresented. Dust absorption further reduced visibility, particularly near the plane of the Milky Way. Even in the clearest regions of sky, plates captured only a fraction of what was truly there. Brightness became the primary filter, whether astronomers intended it or not. Only galaxies above a certain apparent brightness threshold made it into catalogues. Everything fainter effectively did not exist as far as the data were concerned. This is where the idea of the luminosity function enters the story. The luminosity function describes how many galaxies exist at different intrinsic brightness levels. It is not a count of individual galaxies, but a statistical description of a population. Early work on this concept recognized that bright galaxies are rare and faint galaxies are common. The challenge lay in measuring the faint end of that distribution. Fritz Zwicky played an important role in shaping this way of thinking. While studying galaxy clusters in the 1930s, he noticed something peculiar. The motions of galaxies within clusters were far too fast to be explained by the visible mass alone. This led him to propose the existence of large amounts of unseen matter, what is now known as dark matter. Although his ideas were controversial at the time, his approach had broader implications. Zwicky treated galaxies as members of populations rather than isolated curiosities. He considered how many galaxies of different types existed within clusters and how mass was distributed among them. This statistical mindset was essential for counting on cosmic scales. However, early attempts to apply it ran headlong into observational bias. Faint galaxies were not merely undercounted, they were often entirely absent from the data. When astronomers plotted the number of galaxies as a function of brightness using early catalogues, the curve appeared to drop off sharply at low luminosities. It looked as though there were relatively few faint galaxies. That conclusion was comforting, but wrong. The apparent scarcity of faint galaxies was not a feature of the universe, it was a feature of the instruments. Below a certain brightness, galaxies simply vanished from photographic plates. The luminosity function was being truncated by technology, not by nature. This created a systematic bias that was difficult to recognize at first. Because the same bias affected most surveys, results appeared consistent. Different catalogues agreed with one another, reinforcing confidence in their completeness. The missing galaxies were missing everywhere. Bias also crept in through selection choices. Early surveys often focused on visually interesting regions or areas known to contain clusters. Empty regions received less attention. This skewed perceptions of how galaxies were distributed across space. Classification introduced further distortion. Galaxies with clear spiral structure were easy to identify. Elliptical galaxies with smooth light profiles were sometimes mistaken for stars, especially at great distances. Small, diffuse galaxies were often ignored as plate defects or background noise. Even when faint galaxies were detected, their distances were hard to estimate. Without reliable distance measurements, it was difficult to determine whether a faint object was a small nearby galaxy or a large distant one. Many were excluded from counts simply because they could not be placed confidently. All of these factors pushed early galaxy counts downward. The universe appeared simpler and less crowded than it really was. Estimates of the total number of galaxies rose slowly as surveys expanded, but they remained anchored to bright, easily detected systems. The true abundance of faint galaxies remained hidden. There was also an implicit assumption at work. Early astronomers often assumed that the galaxies they could see were representative of those they could not. This assumption seemed reasonable. It allowed small samples to be extrapolated to large volumes. But it relied on the idea that galaxy populations did not change dramatically with brightness or mass. As later observations would reveal, that assumption does not hold. The majority of galaxies are small and faint. Their contribution to the total number is overwhelming, even though their contribution to total light is modest. Early surveys captured the light budget of the universe reasonably well, but they missed much of the population count. This distinction between light and number is subtle but crucial. A small number of large galaxies can dominate the light in a given region of space, while a vast number of small galaxies dominate the count. Counting light is easier than counting objects. Early astronomy, constrained by technology, effectively counted light. The methods themselves embedded this bias. Detection thresholds were fixed by plate sensitivity. Classification schemes favoured well-resolved shapes. Survey areas were chosen for convenience or interest rather than statistical completeness. Each choice seemed practical. Together they shaped the picture of the universe. These early efforts were not failures, they were necessary first steps. They established that galaxies existed in large numbers and that they were not distributed randomly. They introduced the statistical tools that would later be refined and corrected. Most importantly, they revealed that counting galaxies was not a simple act of observation. It was an inference problem. As technology improved, astronomers began to revisit these early catalogues, comparing them with deeper observations. Discrepancies emerged. Regions once thought to be sparse were found to contain many faint galaxies. Clusters appeared richer when observed with more sensitive instruments. Corrections were applied. Luminosity functions were extended toward lower brightness. Biases were quantified and modelled. Each correction pushed galaxy counts upward. The early attempts to count the universe did not produce a final number. They produced a lesson. The number of galaxies one finds depends on how one looks, what one is able to detect, and which assumptions are built into the method. That lesson would guide every later effort, as astronomers moved from photographic plates to digital detectors, from hand-drawn catalogues to automated surveys, and from counting what is obvious to accounting for what is almost invisible. The universe had already been crowded. It was only beginning to be counted. Distance in the universe is never just distance. Every time light travels across space, it also travels across time. This means that looking farther away is the same as looking further into the past. Nearby galaxies are seen as they exist now, shaped by billions of years of evolution. Distant galaxies are seen as they were long ago, often when the universe itself was much younger. This effect is known as look-back time, and it changes the meaning of observation in a fundamental way. When astronomers observe a galaxy 10 million light-years away, they see it as it was 10 million years ago. At 1 billion light-years, the image captures a state from 1 billion years in the past. At even greater distances, galaxies are seen during their earlier stages of formation. As a result, the universe does not present a single, uniform population of galaxies at different distances. It presents a layered history. Nearby galaxies tend to be mature systems. Many have settled into stable structures, with star formation occurring at moderate rates or having largely slowed. Spiral arms are well defined. Elliptical galaxies contain older stellar populations. These galaxies reflect the outcome of long evolutionary processes, including mergers, interactions, and gradual gas depletion. Distant galaxies tell a different story. They are often smaller, more compact, and more irregular. Star formation rates tend to be higher. Structures are less settled. Some appear clumpy or distorted, not because they are abnormal, but because they are young. This intrinsic difference matters deeply for counting galaxies. If distant galaxies were simply farther away versions of nearby ones, counting would be relatively straightforward. One could correct for distance and brightness, then extrapolate. But because galaxies evolve, the distant population is not a mirror of the nearby population. It represents earlier stages in the life cycle of galaxies. This complicates any attempt to estimate how many galaxies exist at a given time. The challenge is compounded by the concept of an observational horizon. In relativistic cosmology, the observational horizon defines the maximum region of the universe from which light has had time to reach an observer since the beginning of cosmic expansion. Beyond that boundary, light has not yet arrived, regardless of how powerful a telescope might be. George Ellis has written extensively about these horizons. emphasizing that they are not physical edges or walls, but limits imposed by time and the finite speed of light. The observable universe is not the entire universe. It is the portion that has had time to reveal itself. This distinction is essential for galaxy counting. Any count is automatically restricted to the observable universe. Galaxies beyond the horizon may exist in enormous numbers, but they cannot be observed directly. They must be excluded from empirical counts, even if theory suggests their presence. Within the observable universe, distance still introduces additional limits. As galaxies recede farther into the past, their light becomes fainter and more stretched. This stretching affects not only the color of light, but also how it is distributed across the sky. One of the most important consequences is surface brightness dimming. Surface brightness refers to how much light is received per unit area on the sky. As distance increases, the total light from a galaxy spreads over a larger area, and the expansion of the universe further reduces the energy of that light. The combined effect causes surface brightness to decrease rapidly with distance. This means that even if a distant galaxy has the same intrinsic brightness as a nearby one, it will appear much fainter per unit area. Extended, diffuse galaxies suffer most from this effect. Their light becomes so spread out that it falls below detection thresholds, even when their total luminosity might be substantial. Compact galaxies fare better. Dense regions of star formation can remain visible at great distances, while extended disks fade into invisibility. This introduces a selection effect that favors certain types of galaxies over others as distance increases. The universe, in other words, becomes biased towards showing only its brightest and densest structures at early times. This bias affects how galaxy populations are interpreted. Surveys of distant galaxies tend to detect small, compact, intensely star-forming systems. Large, diffuse galaxies may exist at those epochs, but their light is too spread out to be detected reliably. As a result, the distant universe appears populated by galaxies that look very different from nearby ones. Some of that difference reflects genuine evolution, some reflects the limits of observation. Separating these effects is difficult, and errors in that separation directly affect galaxy counts. There is another subtlety. The galaxies seen at great distances are not necessarily the ancestors of nearby galaxies in a simple one-to-one way. Many early galaxies merge with others, forming larger systems. Some are destroyed entirely. The number of galaxies decreases over time through mergers, even as the total stellar mass increases. This means that counting galaxies at different distances is not counting the same population at different times. It is counting different snapshots of a changing system. At earlier epochs, the universe contained more galaxies, but they were smaller and more numerous. Over time, mergers reduced their number while increasing their size. The nearby universe contains fewer galaxies, but on average they are larger. This creates a tension in interpretation. Should galaxy counts focus on how many galaxies exist now, or how many have ever existed? These are different questions with different answers. Most observational studies focus on the present-day count within the observable universe. But those counts are informed by data drawn from across cosmic time, requiring careful modelling to translate past populations into present estimates. Light itself becomes a filter. As distance increases, only certain wavelengths remain detectable. Infrared observations become essential for studying distant galaxies, because the light emitted by young stars is stretched into longer wavelengths by cosmic expansion. Before such observations were possible, entire populations of early galaxies were invisible. They were not absent. They were simply shifted out of view. This reinforces a recurring theme. The number of galaxies one can count depends on the properties of light, the age of the universe, and the sensitivity of instruments. It is not a static quantity waiting to be discovered. Look-back time ensures that distance always comes with evolution. Observational horizons ensure that some regions remain permanently inaccessible. Surface brightness dimming ensures that many galaxies fade away before they can be recognized. Together, these effects mean that the distant universe is not just farther away, it is fundamentally harder to interpret. This difficulty does not make galaxy counting impossible, but it demands care. Astronomers must model how galaxy populations change over time, how observational biases distort samples, and how missing faint systems alter the totals. Each correction adds uncertainty. Each assumption carries consequences. Yet despite these challenges, patterns emerge. Galaxy populations grow denser toward the past. Small galaxies become more common. Star formation rates rise. Structures simplify. These patterns provide clues. They allow astronomers to estimate how many galaxies existed at different times and how many remain today within the observable universe. Still, the limits remain. No telescope can see beyond the observational horizon. No observation can escape the influence of time. No image is free from the effects of dimming and selection. Counting galaxies, therefore, is not merely a spatial problem. It is a temporal one. It requires accounting for a universe that changes as it is observed. Understanding this prepares the ground for the next challenge, where distance and time intersect with the expansion of space itself, further reshaping what can be seen and counted. Light carries information, but it does not arrive unchanged. As light travels through the universe, it does more than simply move from one place to another. The space it passes through changes while the light is in transit. This change leaves an imprint on the light itself, stretching it, softening it, and shifting it toward longer wavelengths. This effect is known as redshift, and it is one of the most important observational clues in modern astronomy. Redshift is not something inferred from theory alone, it is measured directly. When astronomers examine the spectrum of light from a distant galaxy, they see familiar patterns of absorption and emission lines, signatures produced by atoms such as hydrogen, oxygen, and calcium. In nearby galaxies, these lines appear at their expected positions. In more distant galaxies, the same lines appear shifted toward the red end of the spectrum. The farther away the galaxy, the greater the shift. This observation tells a clear story. The light has been stretched during its journey, not because the galaxy is moving through space in a conventional sense, but because space itself has expanded while the light was traveling. The wavelength grows along with the universe. This stretching has immediate consequences for visibility. As light is stretched, its energy decreases. The same number of photons is spread across longer wavelengths, making the light dimmer and harder to detect. At great distances, this effect becomes severe. Redshift therefore acts as an observational filter. It does not remove galaxies from existence, but it gradually removes them from view. This understanding was not always accepted. In the early and mid-20th century, astronomers explored alternative explanations for the observed redshifts. Some proposed that light might lose energy as it travelled, a family of ideas sometimes grouped under the term tired light. Others suggested that redshifts might arise from unknown interactions between light and matter. These ideas were considered seriously because the implications of cosmic expansion were profound. If the universe was expanding, then it must have been smaller in the past. That raised uncomfortable questions about origins, timing, and large-scale structure. One of the most influential alternatives was the steady-state theory, developed in part by Herman Bondi, along with Thomas Gold and Fred Hoyle. In this model, the universe expands but maintains a constant average density through the continuous creation of matter. Galaxies form continuously over time, and the large-scale appearance of the universe remains the same forever. The steady-state theory was elegant and philosophically appealing. It avoided a beginning. It preserved a kind of cosmic equilibrium, and importantly for galaxy counting, it implied that galaxy populations were steady over time. If the universe were truly in a steady state, then the number of galaxies per unit volume would remain constant. Observing farther into space would simply reveal more of the same. Galaxy counts would scale smoothly with distance, without dramatic changes in population. This made galaxy statistics a key testing ground. As observations improved, the predictions of steady-state models began to diverge from reality. Deep surveys showed that distant galaxies were not simply more distant versions of nearby ones. Their properties changed with redshift. Star formation rates increased. Galaxy morphologies became more irregular. The universe looked different at earlier times. These changes were difficult to reconcile with a steady-state universe. The final blow came from multiple lines of evidence, including the discovery of the cosmic microwave background and the observed evolution of galaxy populations. Expansion with a hot, dense early universe provided a far better explanation of the data. Once expansion became the accepted framework, redshift took on a new role. It became not just a measure of distance, but a measure of cosmic time and observational limitation. As redshift increases, galaxies are pushed into regimes that challenge detection. Their light moves out of optical wavelengths into the infrared. Their surface brightness drops. Their features blur. At sufficiently high redshift, even large galaxies become faint smudges, and small galaxies disappear entirely. Expansion does not hide all galaxies equally. Compact, intensely star-forming regions can remain visible at great distances because their light is concentrated. Diffuse systems suffer more. Their stretched light falls below detection thresholds long before their compact counterparts. This creates a selective view of the distant universe. Observations preferentially reveal the brightest, densest regions, while extended structures fade away. The farther back one looks, the more incomplete the census becomes. For galaxy counting, this is critical. Expansion means that detectability depends not only on intrinsic brightness, but on how that brightness is distributed and how far the light has travelled. Two galaxies with the same total luminosity can have very different chances of being observed, depending on their size, structure, and star formation activity. Expansion also introduces a practical horizon for observation. Beyond a certain redshift, galaxies are not just faint, they're effectively inaccessible to current instruments. Their light may exist, but it is too stretched, too weak, or shifted into wavelengths that are difficult to observe. This horizon is not fixed. It moves as technology improves. Infrared telescopes extend reach. Larger mirrors collect more light. Better detectors reduce noise. Each advance pushes the observable boundary outward. But the principle remains. Expansion ensures that some galaxies will always lie near or beyond the edge of detectability. As surveys deepen, new galaxies appear, but the population just beyond the limit remains hidden. The steady-state debate highlights why this matters. If galaxy populations were static, missing galaxies would represent a finite correctable error. In an evolving, expanding universe, missing galaxies represent a moving target. The farther back one looks, the more the population changes and the harder it becomes to sample fully. Expansion therefore shapes galaxy counts in two ways at once. It alters the appearance of galaxies through redshift and dimming, and it ensures that the universe being observed is not the universe as it exists now, but as it existed at different stages of its history. This dual effect complicates every estimate. Counting galaxies is not like counting trees in a forest where all trees exist at the same time and are equally visible. It is more like counting waves on an ocean, while the water itself is stretching and changing beneath them. The result is not confusion, but caution. Modern galaxy counts explicitly account for redshift effects. They model how light is stretched. They correct for dimming. They estimate how many galaxies are likely missing at each distance. These corrections are grounded in observation, but they carry uncertainty. Expansion guarantees that uncertainty will never vanish entirely. What it also guarantees is that the universe revealed by observation is filtered by time and space together. Redshift is not a nuisance to be corrected away. It is the mechanism that connects distance, time and visibility into a single framework. Understanding this prepares the way for the next step, where expansion itself sets deeper limits on what can ever be observed, no matter how advanced our instruments become. At a certain scale, counting galaxies one by one simply stops making sense. The sky contains too many objects spread across too much space, changing too subtly with distance and time. Even the most patient observer, armed with the largest telescope, could never compile a complete list by inspection alone. The problem is not effort, it is scale. This is where galaxy counting becomes statistical. Instead of asking how many galaxies can be individually identified, astronomers ask a different question. Given a carefully measured sample of the universe, how many galaxies are likely to exist in total? This shift marks the transition from traditional observational astronomy to statistical cosmology. Statistical cosmology treats galaxies as members of populations rather than as isolated objects. Patterns, distributions, and probabilities become more important than individual examples. The aim is not completeness in the everyday sense, but representativeness. Large-scale surveys make this possible. One of the most influential of these is the Sloan Digital Sky Survey, a long-running project that systematically mapped a significant fraction of the sky using uniform instruments, consistent observing strategies, and carefully controlled calibration. Rather than targeting specific objects of interest, the survey scanned broad regions of sky methodically, recording everything above well-defined detection thresholds. This approach mattered enormously. Uniformity allowed astronomers to understand what the survey was capable of detecting and, just as importantly, what was likely to miss. Every limitation was documented. Every sensitivity curve was measured. Nothing was left to impression. Calibration was central to this effort. Instruments drift over time. Detectors respond differently to different wavelengths. Atmospheric conditions vary from night to night. To correct for this, survey teams repeatedly observed standard stars with known properties. These reference points allowed raw measurements to be translated into reliable physical quantities. Without such calibration, comparisons across the sky would be meaningless. A galaxy appearing faint in one region might simply reflect poorer observing conditions rather than intrinsic properties. Completeness is the next concern. A survey is said to be complete down to a certain brightness if it reliably detects all objects brighter than that limit within its coverage area. Below that limit, detections become incomplete. Some objects are detected, others are missed. Survey teams invest enormous effort in determining where this boundary lies. Artificial galaxies are sometimes injected into data to test detection algorithms. Recovery rates are measured. Detection probability is mapped as a function of brightness, size, and surface brightness. The result is a completeness function, a description of how detection probability changes across different kinds of galaxies. This is where selection functions enter. A selection function describes the probability that a galaxy with specific properties will be included in a survey. It depends on intrinsic brightness, distance, size, shape, color, and surface brightness. It also depends on observational factors such as noise, resolution, and sky background. No survey has a flat selection function. Some galaxies are easy to detect, others are almost invisible. Statistical cosmology works by modeling these biases rather than pretending they do not exist. Once the selection function is known, correction models can be applied. If a certain type of galaxy is detected only half the time at given distance, then the observed number can be adjusted accordingly. If small diffuse galaxies are underrepresented, their expected contribution can be inferred statistically. This does not produce certainty, it produces probability. Instead of saying a survey detected 10,000 galaxies, astronomers say something more careful. Given the survey's sensitivity and selection effects, those 10,000 detections imply a larger underlying population with a certain probability distribution. The language shifts from counting to inference. This approach may feel unsatisfying at first. There is no final tally. There is no clean list, but it reflects the reality of the problem. The universe does not present itself in a way that allows complete enumeration. Probabilistic counting acknowledges that limitation openly. It also allows different surveys to be combined. Surveys covering different wavelengths, depths, and sky areas can be cross-calibrated. Overlapping regions can be compared. Discrepancies reveal biases. Agreements strengthen confidence. The Sloan Digital Sky Survey, for example, mapped millions of galaxies across a broad swathe of the sky, providing an unprecedented statistical foundation. Yet even this vast dataset captures only the brighter portion of the galaxy population. It is extremely good at counting luminous galaxies. It is less complete for faint dwarfs and low surface brightness systems. That limitation is not a flaw, it is a boundary condition. Later surveys build on this foundation by pushing deeper or by observing at different wavelengths. Infrared surveys reveal dust-obscured galaxies. Radio surveys trace gas-rich systems. Each adds a piece to the statistical picture. Crucially, no single survey is treated as definitive. Modern galaxy counts emerge from the synthesis of many surveys, each with known strengths and weaknesses. Models are adjusted until they reproduce the combined observations across multiple datasets. Where models fail, assumptions are revisited. This iterative process is slow, careful, and deliberately conservative. Uncertainty is not something to be eliminated. It is something to be quantified. In statistical cosmology, uncertainty is structural. It arises from cosmic variance, the fact that different regions of the universe are not identical. It arises from observational limits that cannot be removed entirely. It arises from evolving galaxy populations and changing definitions. Even if instruments were perfect, the universe itself would introduce variation. A small patch of sky may contain an unusually rich cluster or an unusually empty void. Extrapolating from that patch carries inherent risk. Surveys mitigate this by covering large areas, but no survey can observe the entire sky at infinite depth. As a result, galaxy counts are always expressed as ranges rather than exact numbers. Confidence intervals accompany estimates. Assumptions are stated explicitly. This is not caution for its own sake. It is a reflection of how the problem behaves. Counting by survey replaces the illusion of completeness with a framework of measured uncertainty. It accepts that some galaxies will always lie below detection thresholds. It acknowledges that correction models rely on assumptions that may evolve with better data. The alternative would be to present precise numbers with unjustified confidence. Astronomy has learned, sometimes painfully, that such precision is often misleading. There is a quiet elegance in this approach. By embracing probability, astronomers gain robustness. Results can be updated as new data arrives without overturning the entire framework. Counts can rise or fall without implying error, only refinement. In this way, large-scale surveys transform galaxy counting from a fragile exercise into a resilient one. The numbers may change, but the method remains sound. The universe is not being counted in the ordinary sense. It is being sampled, modelled, and understood statistically. That shift makes it possible to speak meaningfully about galaxy abundance at all, even in a universe where complete visibility is unattainable. And it sets the stage for deeper observations that push beyond previous limits, revealing galaxies that earlier surveys could only infer. For decades, astronomers wondered what would happen if a telescope simply stopped chasing interesting objects and stared at nothing instead. Not a galaxy cluster, not a bright nebula, just an apparently empty patch of sky, chosen precisely because it looked unremarkable. No known stars, no obvious galaxies, nothing that would normally justify precious observing time. The Hubble Space Telescope made that experiment possible. When the decision was made to point Hubble at such a region and leave it there for days, the goal was not discovery in the traditional sense, it was statistical. The idea was to sample the universe deeply but narrowly, to see what existed below the thresholds of previous surveys, and to measure how crowded space truly was when observed without prejudice. What emerged from that experiment would permanently change how galaxy abundance was understood. As Hubble accumulated light over long exposures, the empty patch of sky filled in. Faint points appeared first, then smudges, then structured shapes, spiral arms, compact blobs, elongated streaks. By the time the image was complete, thousands of galaxies were visible in a region of sky no larger than a grain of sand held at arm's length. This was the Hubble Deep Field. It was not impressive because of any single galaxy. It was transformative because of density. In a tiny area of sky, Hubble had revealed a population of galaxies stretching back billions of years, spanning a wide range of sizes, shapes, and stages of evolution. The implication was immediate and unsettling. If thousands of galaxies existed in such a small patch, then the total number across the entire sky had to be enormous. The deep field was not a special place. It had been chosen precisely because it was ordinary. There was no known cluster there, no reason to expect an unusually high density, which meant that the universe, on average, was far more crowded with galaxies than previously estimated. This was not guesswork. It was a statistical inference. Deep fields function as controlled experiments. By observing a very small area to extreme depth, astronomers can measure the number of galaxies per unit area, down to very faint limits. That density can then be extrapolated cautiously to larger regions of sky. The word cautiously matters. Researchers such as Garth Illingworth played a central role in analysing deep field data, focusing not just on detection, but on interpretation. The challenge was not simply to count galaxies in the image. It was to understand which galaxies were being seen, which were being missed, and how representative the sample truly was. Deep fields are powerful because they reveal faint galaxies that wide surveys cannot detect, but they are also narrow. They sample only a tiny fraction of the sky. Cosmic variance becomes important. A deep field might pass through a slightly denser or slightly emptier region of the universe, skewing the apparent counts. This means that deep fields cannot be treated as literal inventories. They are probes. By combining deep fields from different sky locations, astronomers reduce the risk of overinterpreting any single patch. Repeated experiments refine the statistics. Patterns emerge that are robust against local variation. What consistently emerged was the same conclusion. The number of faint galaxies rose steeply as detection limits improved. There was no obvious cutoff, no point at which the universe suddenly became sparse. Each time Hubble looked deeper, more galaxies appeared. This forced a rethinking of galaxy abundance. Earlier surveys had captured most of the light in the universe, but not most of the galaxies. Deep fields revealed that a large fraction of galaxies contribute very little to the total light budget. They are small, faint, and numerous. This distinction is crucial. Counting light and counting objects are not the same task. The deep field galaxies often appeared irregular and compact, reflecting their youth. Many were undergoing intense star formation. Some would later merge into larger systems. Others would fade or be disrupted. The image was not a census of present-day galaxies alone. It was a layered record of galaxy formation across cosmic time. This introduced another layer of interpretation. When astronomers count galaxies in deep fields, they are counting galaxies as they existed at different epochs. Translating that into a present-day total requires modelling how many of those early galaxies survive as distinct systems, how many merge, and how many disappear. Extrapolation therefore becomes a multi-step process. First, the observed number density is measured. Then corrections are applied for detection limits and surface brightness dimming. Next, evolutionary models are used to connect early populations to later ones. Each step adds uncertainty. None can be skipped. This is why deep field results are not quoted as simple totals. They're expressed as ranges, often spanning factors of several. The numbers are large, but they are not precise. Even so, the paradigm shift was unmistakable. Before deep fields, it was reasonable to imagine that galaxy counts might converge to a stable value as surveys improved. After deep fields, that hope faded. The universe did not reveal a tidy endpoint. It revealed a population that kept growing as sensitivity increased. The Hubble ultra-deep field pushed this further. Even longer exposures revealed galaxies fainter and more distant than those seen before. Each improvement reinforced the same pattern. The faint end of the galaxy population was rich and extended. This did not mean that the universe contained infinite galaxies. It meant that previous counts had been incomplete in systematic ways. Deep fields also demonstrated the importance of wavelength. Optical images captured only part of the picture. Infrared observations revealed additional galaxies whose light had been stretched out of the visible range. Multi-wavelength deep fields showed that different galaxy populations dominate at different epochs. Again, the message was consistency, not chaos. The universe was structured, but that structure was layered and subtle. The deep field experiments did something else equally important. They shifted confidence from individual objects to statistical trends. No single galaxy in a deep field was especially important. What mattered was the collective behavior of thousands. This mindset aligns naturally with probabilistic counting. Deep fields do not promise completeness. They promise depth. They offer a window into populations that are otherwise invisible. The limits of extrapolation remain. A deep field cannot tell us about rare, extremely large structures. It cannot fully sample the largest voids or richest clusters. It cannot see galaxies beyond the observational horizon. But within those limits, it provides a powerful constraint. Any model of the universe that predicts too few galaxies fails immediately when confronted with deep field data. Any model that ignores faint systems collapses under their weight. The deep fields made one thing unavoidable. The universe contains far more galaxies than anyone expected when counting began. Not because the universe changed, but because the tools finally became sensitive enough to reveal what had always been there. After Hubble, galaxy counting could no longer rely on intuition shaped by brightness and prominence. It had to account for the quiet majority. That shift did not close the question of how many galaxies exist. It opened it wider, grounding it in observation while making clear that the answer would always depend on how deeply the universe was willing to be seen. Some galaxies exist at the edge of visibility. They are not small in size. In fact, some are as wide as the Milky Way itself. What makes them difficult to see is not their extent, but their faintness. Their stars are spread so thinly that the glow they produce barely rises above the background of the night sky. These are ultra-diffuse galaxies and low surface brightness galaxies, systems that challenge almost every assumption about what a galaxy looks like. For a long time, these galaxies were effectively invisible. Traditional surveys were designed to detect concentrated light, bright cores, clear edges, distinct shapes. Diffuse systems fail on all counts. Their light is smeared across large areas of sky, making them easy to mistake for background noise, instrumental artifacts, or subtle variations in the sky itself. This is why they were missed for so long. Low surface brightness galaxies are not rare oddities. They're common. They exist in galaxy groups, clusters, and even in relative isolation. Some contain significant amounts of dark matter. Others appear to be almost entirely dominated by it, with very few stars relative to their total mass. Their discovery forced astronomers to confront a bias that had been present all along. Peter van Dokkum played a central role in bringing these systems into focus. Using deep imaging techniques and careful data analysis, his work helped identify large populations of ultra-diffuse galaxies in environments such as the Coma Cluster. These galaxies were astonishing not because they were exotic, but because they were ordinary in number, yet extraordinary in appearance. Some of these systems span tens of thousands of light-years, comparable to large spiral galaxies, yet contain only a tiny fraction of the stars. If placed near the Milky Way, they would be obvious. At greater distances, they fade almost completely from view. This reveals a crucial point. Detectability is not governed by total luminosity alone. It is governed by how that luminosity is distributed. Surface brightness is the key quantity here. A galaxy with its stars packed tightly into a small region produces a strong signal against the background. A galaxy with the same total number of stars spread over a much larger area produces a much weaker signal, even though the total light is the same. This effect becomes severe with distance. As galaxies move farther away, their already diffuse light is further dimmed by the expansion of the universe and spread across fewer detector pixels. Eventually, the signal becomes indistinguishable from noise. Ultra-diffuse galaxies sit precariously close to this boundary even when nearby. At greater distances, they vanish entirely. This explains why early galaxy counts underestimated their numbers so dramatically. Surveys that were highly successful at detecting compact galaxies were systematically blind to diffuse ones. The universe appeared cleaner and simpler than it truly is. When detection methods improved, the picture changed. Deep imaging surveys, careful background subtraction, and targeted searches revealed that ultra-diffuse galaxies are widespread. In some galaxy clusters, they may outnumber large galaxies by significant factors. In groups, they contribute a substantial fraction of the total population. Each new detection quietly inflates the galaxy count. This inflation does not come from discovering galaxies at the edge of the observable universe. It comes from recognizing galaxies that were always there but never registered as galaxies at all. Low surface brightness galaxies also complicate classification. Some appear to contain little or no ongoing star formation. Others host small pockets of young stars. Some are dominated by old stellar populations. Their histories vary widely. What they share is fragility. Diffuse galaxies are particularly vulnerable to environmental effects. In dense clusters, tidal forces and interactions with hot intracluster gas can strip away stars and gas, making these galaxies even fainter over time. Some may survive for billions of years. Others may dissolve into streams of stars, losing their identity as galaxies altogether. This again raises questions about counting. At what point does a galaxy cease to be a galaxy? When its stars are too spread out? When it loses its gas? When its surface brightness falls below detectability? Different answers lead to different totals. Luminosity bias sits at the heart of this problem. Human intuition and early instrumentation favoured bright objects. Astronomers naturally studied what stood out. What barely glowed was overlooked. This bias affects not only discovery, but interpretation. If the universe is sampled primarily through its brightest members, then those members shape expectations. Models are built around them. Counts are extrapolated from them. The recognition of ultra-diffuse galaxies disrupts that approach. It reveals that brightness is not a reliable proxy for abundance. The most common galaxies may contribute very little to the total light of the universe. They hide in plain sight, not because they are distant, but because they are faint. This has a direct impact on estimates of how many galaxies exist. If a large fraction of galaxies are diffuse, then any count based on compact systems alone will be incomplete. Even deep fields, powerful as they are, struggle to detect the most diffuse galaxies at moderate distances. Corrections must be applied. Models must assume populations that cannot be observed directly. Each assumption adds uncertainty, but ignoring these systems adds bias. There is quiet irony here. Ultra-diffuse galaxies are large. They are not small remnants or minor curiosities. They are full-scale galaxies that simply fail to shine efficiently. In a sense, they represent an alternative outcome of galaxy formation, one where dark matter dominates and star formation proceeds inefficiently. Their existence broadens the concept of what a galaxy can be. They also reinforce a recurring theme. The universe contains many more galaxies than it appears to at first glance. Not because galaxies are hiding at unimaginable distances, but because many of them emit their light reluctantly. Counting galaxies therefore becomes an exercise in humility. Each improvement in sensitivity reveals systems that challenge previous assumptions. Each new category widens the population. Ultra-diffuse and low-surface brightness galaxies ensure that the total number of galaxies continues to rise as detection methods improve. They remind astronomers that the universe does not optimize itself for visibility. It simply exists, and much of it barely glows at all. Much of the universe's structure is shaped by something that does not emit light. Galaxies form, grow, and survive inside vast concentrations of dark matter. These concentrations, known as dark matter halos, provide the gravitational scaffolding that allows gas to collect and stars to form. Without them, galaxies as we know them would not exist. Yet dark matter itself remains invisible, detectable only through its gravitational influence. This invisibility introduces a powerful complication when counting galaxies. Astronomers do not observe dark matter halos directly. They observe stars, gas, and dust, then infer the presence of halos from how those visible components move. This means that every visible galaxy is understood to be the luminous tracer of a much larger unseen structure. Halo occupation models formalize this idea. These models describe how galaxies populate dark matter halos of different masses. In simple terms, they ask how many galaxies of various types tend to live inside halos of a given size, and how those galaxies are distributed within the halo. This approach allows astronomers to connect observations to theory. Large halos tend to host large galaxies, often surrounded by smaller satellite galaxies. Smaller halos may host only one faint galaxy or none at all. By measuring galaxy clustering and comparing it to theoretical predictions, halo occupation models help estimate how many halos exist and how many of them should contain visible galaxies. This is where simulations enter the picture. Large cosmological simulations model the growth of structure in the universe from early times to the present. They track how dark matter collapses into halos, how those halos merge, and how their distribution evolves over billions of years. Baryonic processes such as gas cooling and star formation are then added to predict where galaxies should appear. Simon White was instrumental in developing this framework, particularly through his work on structure formation and hierarchical clustering. His contributions helped establish the idea that small structures form first and merge over time to build larger ones. In this picture, the universe naturally produces a vast number of small dark matter halos. The implication is straightforward but unsettling. If dark matter halos are abundant at small masses, then the universe should contain an enormous number of potential galaxy hosts. Yet when astronomers look around the Milky Way, they do not see nearly as many small galaxies as simulations predict. This discrepancy is known as the missing satellites problem. According to simulations, a galaxy the size of the Milky Way should be surrounded by hundreds or even thousands of small dark matter subhalos. Observationally, only a few dozen satellite galaxies are known, even after accounting for recent discoveries of ultra-faint dwarfs. At first glance, this appears to be a failure of the theory. But the issue is more subtle. The simulations predict dark matter structures, not luminous galaxies. Whether a given halo hosts visible stars depends on complex physical processes. Gas may fail to cool efficiently. Star formation may be suppressed by radiation from nearby galaxies. Supernova explosions may expel gas from shallow gravitational wells. As a result, many small halos may remain dark, containing little or no visible matter. They exist, but they do not announce themselves with starlight. This distinction is crucial for galaxy counting. If every dark matter halo hosted a visible galaxy, then galaxy counts would be dramatically higher. Instead, there appears to be a threshold halo mass below which star formation becomes inefficient or impossible. Above that threshold, galaxies form readily. Below it, halos may remain invisible. Determining where that threshold lies is an active area of research. It likely depends on environment, timing, and feedback processes. The threshold may not be sharp. It may be fuzzy, with some halos forming stars while others do not under similar conditions. This uncertainty propagates directly into galaxy estimates. When astronomers use halo occupation models to infer galaxy numbers, they must assume a relationship between halo mass and galaxy formation. Different assumptions produce different results. Some models predict many more faint galaxies than others. Observations constrain these models, but they do not uniquely determine them. The missing satellites problem has softened over time as deeper surveys have revealed more faint dwarf galaxies. The gap between prediction and observation has narrowed, but it has not disappeared entirely. Some halos likely remain completely dark. This raises a fundamental question. Should dark halos without stars be counted as galaxies? Most astronomers answer no. A galaxy, by definition, contains stars. Dark matter halos without visible components are not galaxies, even if they are structurally similar to those that host stars. This decision matters. If galaxy counts are tied to luminous systems, then invisible halos do not contribute directly. But they still shape the population indirectly, by influencing how visible galaxies form, merge, and survive. They are part of the invisible structure underlying the count. Separating inference from observation becomes essential here. Observations tell us how many galaxies we can see, corrected for known biases. Inference tells us how many galaxies likely exist below detection thresholds, based on theoretical models. These are related but not identical statements. When astronomers estimate the total number of galaxies in the observable universe, they combine both approaches. They start with observed populations. They correct for observational limits. They then use models of structure formation to estimate how many galaxies are likely missing. Each step adds uncertainty. It is important to be clear about where the data ends and where the inference begins. Observations anchor the estimates. Theory fills in the gaps. Neither can stand alone. Dark matter ensures that the universe contains far more structure than light alone reveals. But it does not guarantee that all of that structure is populated by stars. The invisible scaffolding is rich. The luminous decoration is selective. This selectivity shapes the galaxy population. In regions where conditions favor star formation, many halos light up. In harsher environments, fewer do. Over time, mergers and feedback further sculpt the population. The result is a universe where the number of galaxies is determined not only by how much structure exists, but by how efficiently that structure produces visible systems. Counting galaxies, therefore, becomes an exercise in restraint. One must resist the temptation to equate structure with luminosity, or to assume that every theoretical object has an observable counterpart. Halo occupation models provide a powerful bridge between theory and observation, but they do not erase uncertainty. They quantify it. The missing satellites problem illustrates this clearly. It is not a sign that something is fundamentally wrong. It is a reminder that galaxy formation is selective, environment-dependent and incomplete. Dark matter gives the universe its architecture. Light fills in parts of that architecture, leaving other regions dark. Galaxy counts reflect where the light has managed to take hold, not the full extent of what exists. Galaxies do not exist outside of time. They are not fixed objects scattered through an unchanging universe. They are processes. Each galaxy reflects a history of assembly, interaction, growth, and loss that unfolds over billions of years. This makes any attempt to count galaxies inseparable from the question of when the counting is done. The dominant framework for understanding this history is hierarchical formation. In this picture, structure builds from the bottom up. Small concentrations of matter collapse first. These early systems merge with others, forming progressively larger galaxies over time. The universe begins crowded with many small galaxies and gradually becomes populated by fewer larger ones. This framework emerged not from speculation, but from observation and simulation working together. In the early universe, galaxies were typically small, gas-rich, and highly active. Star formation rates were intense. Structures were irregular. Mergers were common. These early galaxies did not resemble the well-ordered spirals and smooth ellipticals familiar today. They were unstable, rapidly evolving systems. Over time, mergers reshaped them. Two galaxies colliding do not simply add their stars together. Their gas clouds compress, triggering bursts of star formation. Their orbits change, their shapes distort. Some stars are flung into extended halos or tidal streams, others settle into new configurations. Repeated over cosmic time, this process reduces the total number of galaxies while increasing their average mass. Sandra Faber played a central role in formalizing this evolutionary picture, particularly through work on galaxy scaling relations and the processes that transform star-forming galaxies into quiescent ones. Her research helped clarify how mergers, feedback, and internal dynamics drive galaxies along distinct evolutionary pathways. One of the key insights of this framework is that galaxy counts are epoch-dependent. At early times, the universe contained many more galaxies than it does now, but those galaxies were smaller and less massive. As time passed, mergers reduced their number. A present-day massive galaxy may contain the remnants of dozens or even hundreds of earlier systems. This creates an important distinction. There is the number of galaxies that exist now within the observable universe, and there is the number of galaxies that have ever existed over cosmic history. These are not the same quantity. Most galaxy counts aim to estimate the present-day number, but the data used to infer that number come from observations across time. Deep surveys capture galaxies as they existed billions of years ago. Interpreting those observations requires understanding which of those galaxies survived, which merged, and which disappeared. Some early galaxies vanish completely as independent systems. They are absorbed into larger galaxies, their stars becoming part of a new whole. Others are disrupted, stretched into streams that wrap around their descendants. Their identities are lost even though their material persists. This disappearance is not an anomaly. It is the normal outcome of hierarchical growth. As a result, the universe becomes less crowded in terms of galaxy count, even as it becomes richer in terms of total stellar mass. Fewer galaxies, but larger ones. This time dependence complicates counting in subtle ways. When astronomers observe a deep field, they see a mixture of galaxies from many epochs. Some of those galaxies will still exist today in recognizable form, others will not. Translating observed counts into a present-day total requires models of survival and merger rates. These models depend on environment. In dense regions such as clusters, mergers are frequent. In low-density regions, galaxies may evolve more quietly. A galaxy's fate is shaped as much by where it lives as by its initial mass. This means that galaxy counts vary across cosmic environments as well as across time. A region observed at high redshift may contain many small galaxies that later merge into a handful of large ones. Another region may retain a richer population of small systems. Averaging across the universe smooths these differences, but they never vanish entirely. This introduces uncertainty that cannot be eliminated with better instruments alone. Even with perfect observations, galaxy counts would still depend on modeling how galaxies evolve. The universe does not preserve its population in a way that allows simple accounting. There is also the question of threshold. At what point in its evolution does a system qualify as a galaxy? When it first forms stars, when it reaches a certain mass, when it becomes gravitationally stable. Different answers produce different counts at early times. Early galaxies often formed stars in brief, intense bursts. Some may have flickered into existence and faded again quickly. Should such transient systems be counted? They existed, but briefly. Modern definitions typically require a galaxy to be a long-lived, gravitationally bound system. Applying that definition retrospectively to early epochs is not straightforward. Many early systems do not fit neatly. This again reinforces that galaxy counts are not timeless truths. They are contextual descriptions. Sandra Faber's work helped clarify that galaxy evolution is not a single path, but a network of possible trajectories. Some galaxies grow steadily, others are quenched early, some merge repeatedly, others remain isolated. The diversity of outcomes ensures that galaxy populations change continuously. From a present-day perspective, the universe contains a certain number of galaxies above certain thresholds of mass and brightness. That number reflects the outcome of billions of years of mergers, disruptions, and survivals. From an earlier perspective, the universe contained many more galaxies, but fewer large ones. Both statements are correct. They describe different moments in the same unfolding process. This time, dependence places a natural limit on precision. Any number quoted without reference to epoch is incomplete. The question how many galaxies are there must always be accompanied by when. Most often the implicit answer is now, within the observable universe. But even that now is inferred from light that left galaxies at different times. Counting galaxies therefore becomes an exercise in temporal translation. Observations made across billions of years are stitched together into a present-day estimate using models of evolution. Those models are well constrained in broad terms, but not exact in detail. They capture trends, not individual histories. The result is a range, not a point. Understanding galaxy counts requires accepting that the universe does not keep a ledger. It builds, dismantles, and rebuilds its structures continuously. What exists at one moment is the residue of countless earlier configurations. Galaxies are not conserved entities. They are temporary arrangements of matter and energy shaped by gravity and time. Recognizing this shifts the focus away from seeking a single final number. Instead, it invites a deeper appreciation of how abundance itself evolves. The universe has not always contained the same number of galaxies, and it never will again. Any answer to the question of how many galaxies exist is therefore a snapshot, framed by time, shaped by history, and provisional by nature. That does not make the question meaningless, it makes it honest. At a certain point, the universe becomes too large to observe directly in full detail. No telescope can watch billions of galaxies form, merge, and evolve across cosmic time. No survey can capture every faint system, every interaction, every moment of transformation. To understand how a universe full of galaxies behaves as a whole, astronomers turn to a different tool. They build a universe instead. Large cosmological simulations attempt to recreate the evolution of structure from the earliest moments after cosmic expansion began to the present day. They begin with simple initial conditions, guided by observations of the early universe, and allow gravity, expansion, and physical laws to shape what emerges. These simulations do not draw galaxies by hand. They allow them to form naturally from the collapse of matter under gravity. The backbone of these simulations is dark matter. Vast numbers of simulated particles represent the distribution of dark matter across space. As the simulation evolves, these particles clump together, forming halos, merging, and creating the large-scale web of structure seen in galaxy surveys. Once this dark matter framework is in place, ordinary matter is added. Gas flows into halos, it cools, it collapses, stars begin to form. Over time, galaxies emerge within the simulated universe. Volker Springel has been a central figure in developing these computational approaches, particularly through large-scale simulations that combine dark matter dynamics with models of galaxy formation. His work helped demonstrate that it is possible to reproduce many of the statistical properties of the observed universe using physically motivated rules. These simulations are not small. They often track billions of particles across volumes hundreds of millions of light-years wide. They require vast computational resources and months of processing time. Each run produces enormous datasets that must be analyzed carefully. Despite their sophistication, these simulations face an unavoidable limitation. They cannot resolve everything. The processes that govern star formation, supernova explosions, black hole growth, and gas turbulence occur on scales far smaller than the resolution of even the largest simulations. It is not possible to calculate these processes from first principles at every point in the simulated universe. Instead, simulations rely on what are known as subgrid models. Subgrid models describe how small-scale physics behaves on average within a larger region. They are informed by detailed observations and smaller simulations, but they remain approximations. They specify, for example, how efficiently gas turns into stars under certain conditions, or how much energy a supernova injects into its surroundings. These choices matter. Changing a subgrid prescription can alter the number of galaxies that form, their sizes, their brightness, and their survival rates. Small changes at the microscopic level can ripple outward, reshaping the macroscopic population. This introduces a fundamental humility into simulation-based counting. When a simulation predicts a certain number of galaxies above a given mass or brightness, that number reflects both the underlying physics and the assumptions embedded in the model. Agreement with observation is meaningful, but it is not absolute proof. Disagreement is informative, but not necessarily failure. What matters is the pattern. Modern simulations successfully reproduce many large-scale features of the universe. They match the clustering of galaxies. They reproduce the distribution of galaxy masses. They capture the emergence of filaments, voids, and clusters. When simulations and observations agree on these broad trends, confidence grows that the underlying framework is sound. At the same time, tensions remain. Some simulations predict more small galaxies than are observed. Others struggle to reproduce the correct number of massive galaxies at certain epochs. The precise balance between star formation and feedback remains an active area of refinement. These tensions are not embarrassing. They are productive. They highlight where understanding is incomplete. They point to physical processes that may be missing or misrepresented. They guide new observations and motivate improved models. From the perspective of galaxy counting, simulations serve a specific role. They provide a way to estimate populations that cannot be observed directly. They suggest how many galaxies should exist below detection thresholds. They predict how galaxy numbers should change with time and environment. But they do not replace observation. A simulated galaxy is not a detection. It is a hypothesis about what should exist, given a set of assumptions. Observations test those hypotheses. When the two diverge, the assumptions are revisited. This back and forth between simulation and observation is central to modern cosmology. It ensures that galaxy counts are not extrapolated blindly. They are constrained by data at every step. Simulations are adjusted until they reproduce what is seen, and then used cautiously to explore what is unseen. There's also a deeper lesson here. Simulations reveal that the universe naturally produces complexity. Even with simple initial conditions and well-understood laws, the outcome is rich, varied, and sensitive to small changes. Galaxy populations are not fine-tuned to simplicity. This reinforces why galaxy counts resist precision. The universe does not contain a neat, evenly spaced collection of galaxies. It contains a hierarchy of structures shaped by chance encounters, feedback loops, and environmental effects. Simulations capture this messiness, not eliminate it. When astronomers quote estimates for the total number of galaxies, they often rely on simulations to fill in the faint end of the population. But they do so with caveats. The numbers are conditional. They depend on how star formation behaves in low-mass halos. They depend on feedback efficiency. They depend on how galaxies respond to their surroundings. All of these dependencies are areas of ongoing research. Volker Sprengel and others have emphasized that simulations are tools for understanding, not oracles. They help explore possibilities. They clarify relationships. They expose sensitivities. They also remind us of limits. No simulation can capture every detail. No model can include every process at full resolution. There will always be uncertainty at the smallest scales, and those uncertainties will propagate upward. This does not undermine the value of simulations, it defines it. By comparing simulated universes to the real one, astronomers learn which assumptions are reasonable and which are not. They learn where confidence is warranted and where caution is required. In the context of galaxy counting, simulations provide a vital complement to observation. They help bridge the gap between what can be seen and what likely exists, but they do not deliver a final number. Instead, they reinforce a pattern that has emerged again and again. Every time the universe is examined with greater depth or broader scope, it reveals more structure than expected. Not because it is deceptive, but because it is generous. Simulating a universe full of galaxies does not simplify the counting problem, it deepens it. And in doing so, it reminds us that understanding abundance is less about reaching closure and more about refining perspective, one assumption at a time. At some point, the question stops being how many galaxies exist in principle and becomes how many can actually be observed today. This distinction matters. The observable universe is not defined by imagination or theory, but by light that has had time to reach us and by instruments capable of detecting it. Within those limits, astronomers attempt to estimate how many galaxies are present right now, acknowledging that any answer is provisional and conditional. Modern observational studies tend to converge on large ranges rather than single numbers, depending on how faint a system must be to qualify as a galaxy, and how aggressively corrections are applied for unseen populations. Estimates for the number of observable galaxies typically span from hundreds of billions to several trillion. This spread is not a sign of disagreement about basic facts. It reflects methodological differences. Some surveys focus on counting galaxies directly detected in deep imaging, then extrapolate cautiously to account for incompleteness. Others incorporate results from simulations, halo occupation models, and luminosity functions to infer how many galaxies likely exist below detection thresholds. Each approach rests on different assumptions about galaxy formation, survival, and detectability. Christopher Consolis has been central in synthesizing these approaches, combining deep field observations with statistical corrections to estimate the total number of galaxies within the observable universe. His work emphasized that earlier counts had dramatically underestimated galaxy abundance by missing faint, small, and diffuse systems. One of the key insights from this synthesis is that sensitivity drives the count. As telescopes become more sensitive, they do not simply refine existing numbers, they reveal entirely new populations. Each improvement in depth uncovers galaxies that were previously invisible, especially at the low mass and low surface brightness end of the population. This creates a predictable pattern. Galaxy counts rise as surveys deepen. They do not plateau cleanly. The reason lies in the shape of the galaxy luminosity function. Bright galaxies are rare, Faint galaxies are common. The number of galaxies increases steeply as intrinsic brightness decreases. Missing even a small range at the faint end can remove a vast number of galaxies from the count. Early surveys captured most of the light in the universe, but not most of the galaxies. Modern surveys push deeper, capturing more of the population, but still not all of it. Different surveys also probe different wavelengths. Optical surveys excel at detecting galaxies with active star formation. Infrared surveys reveal dust-obscured and high redshift systems. Radio observations trace gas-rich galaxies that may be faint in visible light. No single survey captures the full diversity. Combining these datasets requires careful cross-calibration. Objects detected in one wavelength may be missed in another. Selection functions differ. Corrections must be applied consistently. Even then, uncertainty remains. Cosmic variance plays a role. A deep field may sample a region that is slightly overdense or underdense compared to the cosmic average. Large area surveys reduce this effect but cannot eliminate it entirely. There is also the issue of classification. Some faint systems sit near the boundary between galaxies and star clusters. Including or excluding them changes the count. Reasonable researchers can make different choices without error. When modern studies quote numbers on the order of a few trillion galaxies, they are not claiming to have counted each one. They are stating that given current observations and models, this is the most plausible range for how many galaxies exist within the observable universe today. The phrase "within the observable universe" is doing important work here. It excludes galaxies beyond the observational horizon, which cannot be seen or counted directly. It also excludes dark matter halos without stars, which are not classified as galaxies under standard definitions. Within those bounds, the uncertainty is not trivial, but it is constrained. The lower end of estimates corresponds to conservative assumptions about the faint end of the galaxy population. The higher end assumes that many small and diffuse galaxies remain undetected, even in the deepest surveys, consistent with simulation predictions and local group studies. What is striking is not the exact number, but the scale. Even the most conservative modern estimates place the number of observable galaxies far above what was imagined a century ago. The universe is not sparsely populated with a few majestic systems. It is crowded with vast numbers of modest ones. This conclusion is robust across methods. Whether one starts from deep field counts, luminosity functions, or simulation-informed corrections, the same qualitative picture emerges. Galaxies are abundant. Faint galaxies dominate the numbers. Detectability, not existence, sets the limits. This is where conditional certainty comes in. Astronomers are confident about trends, distributions, and orders of magnitude. They are less confident about exact totals. That imbalance is appropriate. The data support broad conclusions, not precise inventories. When the number changes from hundreds of billions to trillions, it is not because earlier work was wrong. It is because new sensitivity reveals new populations, forcing revisions. This process will continue. Future telescopes will push detection limits further. New surveys will reveal galaxies even fainter and more diffuse than those known today. Counts will rise again, not because the universe has changed, but because the view has improved. So how many galaxies can be observed today? The honest answer is a range, not a figure. A range grounded in observation, constrained by theory and shaped by detection limits. Within the observable universe, there are at least hundreds of billions of galaxies, and very likely many times that number. The exact total depends on how faint one is willing and able to look. That uncertainty is not a weakness. It is a reflection of how the universe presents itself. The universe is generous with structure. but selective with visibility. And every time sensitivity improves, it reminds us that abundance was never the limiting factor. Only perception was. The arrival of the James Webb Space Telescope did not rewrite the story of galaxy counting. It sharpened it. From the beginning, Webb was designed to see what earlier telescopes could not. Its strength lies in infrared sensitivity, allowing it to detect light that has been stretched far beyond the visible range by cosmic expansion. This makes it especially powerful for observing distant galaxies whose light began its journey when the universe was young. Before Webb, much of the early universe was inferred rather than seen. Galaxies at very high redshift were detected only in small numbers, often near the limits of confidence. Their properties were uncertain. Their abundance was extrapolated cautiously. Webb changed the balance of evidence. By observing in the infrared with unprecedented sensitivity and resolution, Webb revealed galaxies that had previously slipped below detection thresholds. Many of these systems are faint, compact, and surprisingly numerous. They appear at epochs when the universe was only a few 100 million years old, a period once thought to be sparsely populated with galaxies. These early observations did not come from a single dramatic image or headline result. They emerged from careful analysis by multiple research teams working independently, comparing data across fields, calibrating measurements, and testing assumptions. The emphasis was not on spectacle, but on consistency. What these teams found was not chaos, but continuity. The early universe appears rich in small galaxies, just as models of hierarchical formation predict. Webb did not suddenly reveal a universe overflowing with unexpected giants. Instead, it filled in the faint end of the population, revealing systems that were always expected to exist, but had not yet been observed directly. This matters for counting. Webb does not allow astronomers to count all galaxies directly. It does not eliminate observational horizons. It does not bypass surface brightness dimming. What it does is tighten constraints. It reduces the gap between what is observed and what is inferred. By detecting galaxies at earlier times and lower luminosities, Webb improves estimates of how many galaxies formed in the early universe. Those estimates, in turn, inform models of how many galaxies survive to the present day, and how many merge or disappear along the way. The revisions are indirect but significant. When Webb reveals that faint galaxies are more common at high redshift than previously measured, it suggests that earlier surveys underestimated early galaxy abundance. That does not automatically increase the present-day count, but it changes the inputs used to model galaxy evolution. More early galaxies imply more mergers, more hierarchical growth, and potentially more remnants embedded in today's massive galaxies. It also implies that some early galaxies may persist as faint systems today, contributing to the low luminosity population. Webb also clarifies the role of wavelength in detection. Many early galaxies emit most of their light in ultraviolet wavelengths due to intense star formation. By the time that light reaches Earth, it has shifted into the infrared. Optical telescopes simply could not see it. This does not mean those galaxies were invisible in principle. They were invisible to certain instruments. Webb's infrared vision reveals a population that bridges the gap between theory and observation. It confirms that early galaxy formation was efficient and widespread, not rare or exceptional. At the same time, Webb reinforces familiar limitations. Even with its sensitivity, Webb observes only small regions of sky in extreme depth. It does not provide an all-sky census. Cosmic variance remains a concern. Some deep fields appear richer than others. Statistical interpretation is still required. Webb's discoveries therefore feed into the same probabilistic framework established by earlier surveys. They do not replace it. The difference lies in confidence. With Webb, astronomers are less reliant on extrapolation alone at high redshift. They can measure luminosity functions more directly. They can observe the shapes, sizes, and stellar populations of early galaxies rather than inferring them from faint smudges. This reduces uncertainty at one end of the problem while leaving other uncertainties intact. Webb has also revealed that some early galaxies are more massive and more chemically evolved than expected at their observed epochs. These findings sparked initial surprise, but careful analysis showed that they remain consistent with revised models of rapid early star formation, rather than requiring a fundamental rethinking of cosmology. This pattern is instructive. Webb does not overturn existing frameworks, it refines them. It exposes where assumptions were conservative. It highlights where models need adjustment, not abandonment. For galaxy counting, this means that estimates continue to rise at the margins rather than jumping discontinuously. The universe revealed by Webb is richer, but not alien. There is an important psychological shift here. Public discussion often frames new telescopes as revolution machines, poised to demolish old ideas. In practice, progress is more incremental. Webb's results sit comfortably within the trajectory established by deep fields, simulations, and statistical surveys. Each new population discovered was anticipated in some form. Webb simply makes it visible. This continuity matters because it reinforces trust in the methods used to estimate galaxy abundance. When new instruments confirm rather than contradict the broad picture, confidence in the underlying framework grows. The broad picture is this: galaxies are numerous. Faint galaxies dominate by number. Early galaxies were abundant, many merged, some survived. Detection limits, not existence, set the boundaries of observation. Webb strengthens every part of that picture. It does not answer the question of how many galaxies exist with finality. It narrows uncertainty. It improves calibration. It reveals populations that push counts upward in controlled ways. Future analyses will incorporate Webb's data into luminosity functions, merger histories, and halo occupation models. Estimates will be revised again. The numbers may increase. The ranges may tighten. But the character of the answer will remain the same. There will still be a range rather than a point. There will still be assumptions. There will still be galaxies below detection thresholds. What Webb changes is not the nature of the uncertainty, but the scale of confidence. The universe appears once again to be generous with galaxies and consistent with its own history. Webb does not close the book on galaxy counting. It adds more pages, written in finer detail, without changing the story's direction, and that is perhaps its most important contribution. It shows that deeper vision does not simplify the universe. It reveals it more fully, while preserving the quiet truth that no matter how far instruments reach, some structure will always remain just beyond the edge of sight. There comes a point where the question is no longer about what has been missed, but about what can never be seen. Not because telescopes are insufficient or surveys incomplete, but because the structure of the universe itself sets limits on observation. These limits are not technological. They are causal. The universe has a finite age and light travels at a finite speed. Together, these facts define a boundary known as the cosmic horizon. It marks the greatest distance from which light has had time to reach us since cosmic expansion began. Anything beyond that boundary has not yet had the opportunity to communicate its existence. This horizon is not an edge in space. It is an edge in time. Galaxies beyond it may exist. They may be numerous. They may resemble the galaxies we see nearby, or differ in ways that cannot be tested. What matters is that their light has not arrived and may never arrive, no matter how long one waits. This introduces an important distinction. Some galaxies are unseen because they're too faint, too diffuse, or too distant for current instruments. These galaxies are unseen, but not unreachable. With better sensitivity, longer exposures, or different wavelengths, many of them can be revealed. Other galaxies are unreachable. They lie beyond the causal horizon in regions of space whose light has not reached Earth, and whose future light may never do so, depending on the continued expansion of the universe. These regions are not hidden behind dust or noise. They are separated by the structure of space-time itself. This distinction matters deeply for how galaxy counts are interpreted. When astronomers estimate how many galaxies exist, they are careful to specify that the count applies to the observable universe. This is not a philosophical caveat, it is a physical constraint. The observable universe is the portion of the cosmos that can, in principle, be studied using light or other signals. Beyond it lies more universe, but not more data. It is tempting to ask what lies beyond the horizon. It is also tempting to extrapolate. If the observable universe contains hundreds of billions or trillions of galaxies, then perhaps the unobservable regions contain more of the same. This may be true, but science proceeds cautiously here. The laws of physics appear consistent across the observable universe. Large-scale structure shows statistical uniformity when averaged over vast distances. These observations support the idea that regions beyond the horizon are not fundamentally different. Even so, this remains an inference, not an observation. There is a critical difference between extending a pattern within observed data and claiming certainty about what lies forever beyond reach. The former is a controlled assumption. The latter is speculation. For this reason, astronomers avoid statements about the total number of galaxies in the entire universe. They restrict themselves to what can be observed, modelled, and constrained by data. This restraint is not a lack of imagination, it is methodological discipline. Causal horizons also evolve over time. As the universe ages, light from more distant regions reaches us. The observable universe grows. Galaxies that were once beyond reach become observable, not because they moved closer, but because time has allowed their light to arrive. At the same time, cosmic expansion introduces a competing effect. Some regions of space are receding so rapidly that light emitted today will never reach us in the future. Those regions lie beyond what is sometimes called the event horizon. They are not merely unobserved, they are permanently inaccessible. This creates a subtle asymmetry. The observable universe grows, but not without limit. There are regions that will remain forever outside our observational domain. Galaxies within those regions cannot be counted, catalogued, or confirmed. They are not missing data points. They are inaccessible in principle. This is why careful discussions of galaxy abundance stop where observation stops. They do not invoke infinity. They do not speculate freely beyond causal limits. They acknowledge what is known, what is inferred, and what is fundamentally unknowable. This approach preserves clarity. Unseen galaxies within the observable universe represent an incomplete census. They motivate deeper surveys, better instruments, and improved models. Unreachable galaxies lie in a different category altogether. They do not motivate better observation. They motivate humility. It is also important not to conflate size with reach. The observable universe is vast. Its diameter spans tens of billions of light-years. Within it, there is room for extraordinary numbers of galaxies. The fact that some regions are beyond reach does not diminish the richness of what can be studied, nor does it imply that the observable universe is atypical. All available evidence suggests that the observable universe is a fair sample of the larger whole, at least in statistical terms. But this remains an assumption grounded in observation, not a demonstrable fact about everything that exists. Avoiding infinity claims is part of this discipline. Statements about infinite numbers of galaxies sound impressive, but they do not arise from measurement. They arise from extrapolating beyond the domain where evidence applies. In science, such statements are treated with caution. The universe may be infinite. It may be finite but unbounded. It may have a structure that does not conform neatly to either category. Current observations cannot decide this question conclusively. What can be said with confidence is this: within the observable universe, there are vast numbers of galaxies, far more than early astronomers imagined. Their abundance is supported by multiple independent lines of evidence. Their diversity is well established. Their distribution follows understandable patterns shaped by physics and time. Beyond the observable universe, there is silence, not emptiness, but absence of information. This silence is not frustrating, it is clarifying. It draws a boundary around what science can responsibly address. It reminds us that some questions do not have answers because they do not have access. Counting galaxies, therefore, is not about reaching for the absolute. It is about describing what can be known within the limits set by nature itself. The observable universe offers more than enough complexity to occupy generations of inquiry. Beyond it lies a continuation that may never be tested. Maintaining that distinction allows galaxy counts to remain grounded, meaningful, and honest. It also reframes the original question: how many galaxies are there? Within reach, the answer is vast, conditional, and improving. Beyond reach, the only correct response is restraint, and in that restraint there is a quiet strength. At the end of all the surveys, simulations, and revisions, the number itself can begin to feel misleading. Hundreds of billions, trillions, vast quantities that stretch language until it starts to lose its grip. It is tempting to treat these figures as answers, as if the goal of the exercise were to land on a single, authoritative total. But that has never really been what galaxy counts are for. The number does not represent a final inventory. It represents a description. Every estimate of how many galaxies exist is inseparable from the method used to obtain it. Change the depth of a survey, and the number changes. Change the wavelength, and the number changes again. Adjust the definition of what qualifies as a galaxy, and the total shifts, sometimes dramatically. This is not a flaw in the process. It is the process. Galaxy counts are method-dependent descriptors. They summarize what a particular combination of instruments, assumptions, and corrections reveals about the universe. They are statements about visibility, classification, and inference, not declarations of absolute fact. This is why ranges replace exact totals. When astronomers report that there are likely between hundreds of billions and several trillion galaxies within the observable universe, they are not hedging. They are being precise in the only way the problem allows. The range captures uncertainty that cannot be eliminated without pretending to know more than observation permits. Exact numbers imply closure. Ranges acknowledge limits. Those limits are not just technological, they are epistemic. There are limits to what can be known, even in principle, about a universe observed from one location, at one moment in time, using light that arrives with delays measured in billions of years. Some galaxies are faint enough to escape detection. Some lie in regions of space that will never be observed. Some existed only briefly before merging into larger systems. No amount of improved instrumentation can fully erase these constraints. This does not mean knowledge is shallow. It means it is conditional. Galaxy counts depend on definitions of galaxies, on models of evolution, on corrections for what cannot be seen, and on assumptions about what lies just beyond detection thresholds. Each of these elements is grounded in evidence, but none is exact. Together they produce a picture that is robust in scale and structure, even if imprecise in detail. That robustness is the point. The value of galaxy counts lies not in the last digit, but in the order of magnitude. Not in whether the number is 2 trillion or 3 trillion, but in the recognition that the universe is extraordinarily rich in structure. A century ago, the number of known galaxies was 0. A few decades later, it was measured in dozens, then thousands, then millions. Each increase reflected not a changing universe, but a changing view. Today's numbers continue that trajectory. They tell us that galaxies are not rare, isolated islands. They are the dominant units of visible structure in the cosmos. They populate space densely at small scales, even as vast distances separate them at large scales. They also tell us something quieter, that the universe does not yield to enumeration in the way everyday objects do. It resists being totaled cleanly. Every attempt to count reveals new categories, new edge cases, new subtleties that complicate the picture. Precision gives way to perspective. This shift can feel unsatisfying if the expectation is a single, definitive answer, but it becomes deeply satisfying when the goal changes from certainty to understanding. The number of galaxies is not a score to be settled. It is a summary of how observation, theory, and limitation intersect. When astronomers revise estimates upward, they are not correcting mistakes so much as incorporating previously unseen structure. When they quote uncertainty, they are not admitting ignorance so much as respecting the boundary between data and assumption. In this sense, galaxy counts function as a mirror. They reflect the reach of instruments. They reflect the maturity of theory. They reflect how carefully uncertainty is handled. They even reflect philosophical restraint, the decision to stop where evidence stops. Scale matters more than precision here. Whether the observable universe contains hundreds of billions or several trillion galaxies, the implication is the same. The cosmos is populated on a scale that overwhelms intuition. It contains far more structure than can be held comfortably in mind, even when reduced to numbers. And yet those numbers are meaningful. They anchor imagination. They constrain models. They remind us that the Milky Way is one among an immense population, not a central fixture. What the number really represents, then, is not an answer to a counting problem, but a statement about abundance under constraint. It says that within the limits of what can be observed, corrected, and responsibly inferred, the universe is lavish with galaxies. It also says that certainty has a boundary, and that science is strongest when it marks that boundary clearly, rather than pretending it does not exist. As the discussion draws toward closure, that perspective matters more than any figure. The question of how many galaxies there are does not resolve into a tidy conclusion. It resolves into an appreciation of scale, method, and limit. And in that resolution, something important happens. The universe becomes neither fully known nor fundamentally mysterious. It becomes intelligible in parts, bounded in others, and open to continued refinement. That balance, more than any number, is what the count ultimately represents. Counting galaxies has never been a task with an endpoint. From the moment astronomers realized that the Milky Way was only one system among many, the act of counting became inseparable from discovery itself. Each improvement in observation changed not only the number, but the meaning of the number. What began as a question of how many objects could be seen slowly became a question of how scientific knowledge grows. Counting in this context is not bookkeeping, it is an evolving scientific process. At every stage, galaxy counts have reflected the tools available, the definitions in use, and the assumptions considered reasonable at the time. Early counts were shaped by naked eye observations and photographic plates. Later counts depended on digital detectors, statistical surveys, and computational models. Today's estimates draw on infrared telescopes, deep fields, simulations, and carefully quantified uncertainty. At no point has the universe offered a final answer. Instead, it has offered partial views that improve gradually, sometimes unevenly, as methods advance. What changes is not just how many galaxies are thought to exist, but how confidently different parts of the population can be described. This is why a revision is not a weakness of galaxy counting. It is its defining strength. When estimates rise, it does not mean earlier astronomers were careless or mistaken. It means they were working honestly within the limits of their evidence. As those limits expanded, so did the count. Each revision records progress rather than failure. Humility is built into this process. Astronomers are careful to distinguish between what is observed directly and what is inferred statistically. They separate detectable galaxies from predicted populations. They acknowledge that some systems will always remain below detection thresholds, while others lie beyond causal reach altogether. This restraint is not pessimism, it is precision. Scientific counting advances by marking boundaries clearly. It does not blur the difference between evidence and extrapolation. It does not claim completion where none exists. There is also continuity in this process. Modern galaxy counts, for all their sophistication, still rest on the same basic principle that guided early work. They begin with the Milky Way. Distances are calibrated locally. Galaxy types are understood by comparison with nearby examples. The structure of the local group informs models applied across cosmic volumes. In this sense, the counting always returns home. Even now, uncertainties in the Milky Way's mass, extent, and satellite population influence broader estimates. Discoveries of new dwarf galaxies nearby still alter expectations for what might exist elsewhere. The nearest galaxy remains a reference point, not a solved problem. This circularity is not a flaw. It is a reminder that knowledge is anchored. The universe is not surveyed from the outside. It is studied from within one galaxy, at one moment in time, using signals that arrive late and incomplete. Every count carries that perspective with it. Seen this way, galaxy counting becomes less about totals and more about process. It is a dialogue between observation and theory. Surveys reveal patterns, models attempt to explain them, discrepancies prompt refinement, new instruments reopen questions that seem settled. Numbers shift, not randomly, but in response to improved understanding. There is no expectation that the process will end. Future telescopes will detect fainter galaxies. New surveys will explore wider areas with greater sensitivity. Simulations will incorporate more detailed physics. Definitions may evolve again as new classes of objects blur existing categories. Each step will add structure, not closure. This openness is not unsettling, it is stabilizing. It ensures that conclusions remain proportional to evidence. It prevents numbers from hardening into dogma. It keeps the science responsive rather than rigid. In everyday life, counting implies completion. Once all objects are tallied, the task is finished. In cosmology, counting is different. The act of counting exposes new layers of complexity that make further counting necessary. The universe does not resist being understood, but it does resist being finalized. Ending where the story began brings this into focus. The Milky Way still arcs across the night sky as a faint band of light. It still feels singular from the inside. It still hides parts of itself behind dust, distance, and dark matter. Even here, completeness remains out of reach. And yet, from that imperfect vantage point, astronomers have inferred a universe filled with galaxies beyond imagination. Not through certainty, but through careful accumulation of evidence. Not through final answers, but through a process that refines itself over time. Counting galaxies, then, is not about pinning down the universe. It is about learning how to ask large questions responsibly, how to revise answers without embarrassment, and how to remain grounded while dealing with scales that exceed intuition. The universe, in this sense, remains unfinished, not because it is incomplete, but because understanding it is an ongoing activity rather than a destination. The numbers will continue to change, the methods will continue to improve, the picture will continue to sharpen at the edges. What remains constant is the approach. Careful observation, explicit limits, willingness to revise, respect for uncertainty. That is what galaxy counting ultimately represents. Not a final tally of what exists, but a record of how far understanding has come, and a reminder that even at cosmic scales, knowledge advances one measured step at a time. The Milky Way turns quietly within a vast population of galaxies, none of them fully counted, all of them part of a universe that does not demand completion in order to be understood. And in that unfinished state, the science remains both grounded and open, exactly where it needs to be. There is now no serious doubt about the broad picture. Galaxies are not rare features scattered thinly across space. They are the primary units of visible structure in the universe. They form wherever matter collects inside dark matter halos. They grow, merge, fade, and sometimes disappear. They populate the observable universe in extraordinary numbers, far beyond what early astronomy ever imagined. That much is firmly established. What has also become clear is why no final number exists. Every method used to count galaxies depends on limits of sensitivity, limits of resolution, limits imposed by distance, time, and the expansion of space itself. Even definitions matter. What qualifies as a galaxy at one scale or epoch may blur into something else at another. These are not temporary obstacles waiting to be removed by better technology. They are structural features of how the universe can be known from within. Uncertainty, in this context, is not a failure to decide. It is an honest reflection of the problem's shape. When astronomers quote ranges rather than totals, they are not avoiding commitment. They are committing to evidence rather than impression. They are stating clearly where observation ends and inference begins. They are choosing accuracy over false precision. This is appropriate, not disappointing. Because what matters most is not the last digit, but the scale. The universe contains at least hundreds of billions of galaxies within the observable region, and very likely many more. Faint galaxies dominate the population. Large luminous galaxies like the Milky Way are impressive, but statistically uncommon. Most galaxies are small, dim, and easily missed unless observation is pushed to its limits. That conclusion holds across methods. It holds whether one starts from nearby dwarf galaxies, deep field surveys, statistical corrections, or cosmological simulations. It holds whether one looks backward in time or outward in space. It holds whether one counts directly or infers carefully. Galaxies are common. They are the ordinary outcome of cosmic structure formation, not rare accidents. Wherever conditions allow matter to collapse and cool, galaxies tend to appear. The universe does not produce a few masterpieces. It produces an abundance of modest systems. This abundance reshapes perspective. From inside a single galaxy, space feels vast and empty. Stars are separated by immense distances. Other galaxies appear remote, faint, and sparse. Yet when viewed statistically, the universe is crowded at small scales, dense with structure that only thins when distances become enormous. This contrast between experience and reality is one of astronomy's quiet lessons. Another is restraint. There is a natural temptation to ask for a final answer, a single number that resolves the question once and for all. But the universe does not cooperate with that expectation. It reveals itself gradually, unevenly, and with boundaries that cannot be crossed. Some galaxies are unseen but discoverable. Others lie beyond causal reach. Some existed only briefly before merging into larger systems. Others persist quietly at the edge of detectability. No census can capture all of these simultaneously. Recognizing this does not weaken understanding, it strengthens it. It allows knowledge to remain proportional to evidence. It prevents the mistake of treating estimates as inventories. It keeps the focus on what is known securely, rather than what is merely tempting to assert. In this sense, galaxy counts serve a purpose beyond enumeration. They reveal how scientific knowledge works at extreme scales. They show how observation, theory, correction, and revision interact. They demonstrate that uncertainty can be a sign of maturity rather than confusion. The universe, as it turns out, does not demand final numbers in order to be understood meaningfully. What it offers instead is a stable, consistent picture at the level that matters most. A universe where galaxies are numerous, structured, and shaped by well-tested physical processes. A universe where abundance is not in doubt, even if totals remain open. There is calm in that recognition. The question of how many galaxies there are does not hang unresolved in an uncomfortable way. It rests where it should, supported by evidence and bounded by limits. It does not require speculation beyond what observation allows. The Milky Way continues to orbit quietly within this vast population, one galaxy among many, neither central nor special in number, only familiar by proximity. From this vantage point, the universe feels both immense and intelligible. It doesn't need to be finished to be meaningful. Knowing that the cosmos contains more galaxies than can be easily counted does not diminish understanding. It deepens it. It replaces the desire for closure with an appreciation of scale, method, and restraint. The universe is not withholding a final tally. It is inviting careful attention, and that attention, measured and grounded, is enough. The picture is clear where clarity is possible. The uncertainty remains where uncertainty belongs. Between those two, the universe reveals itself as abundant, structured, and calmly beyond the need for final numbers.